the students who might be watching us later. So good morning, everyone. Welcome to your first office hours. We're going to work on homework number 1. If you guys could, let me lock speaker view here. If you guys could set up your paper with your name, definitely write down homework number 1. So it's just kind of instinct when people used to hand in physical papers to me. I liked it all labeled so I know what I was looking at. Don't forget to put somewhere on the page that you are part of AS1010. That should be obvious when I'm grading you guys, but just do it anyways out of habit, okay? And then I wrote down the problems that we're going to work on. You can write them down too if you want. Tim is going to start us off, and he's going to read the first one. I like to have you guys take turns reading the problems so I can think about them with you, and I can write down some of the information that's necessary. So what's our first one ask for us, Tim?
Says investigate further. Short answer / essay question. 44. New planet. A planet in another solar system has a circular orbit and an axis tilt of 35 degrees. Would you expect this planet to have seasons? If so, would you expect them to be more extreme than the seasons on Earth? If not, why not?
Okay. So we have a new planet. It's got a circular orbit. It has an axis tilt of 35 degrees, which is different than Earth's, right? Do you guys remember what Earth's axis tilt is? Someone up there remember Earth's axis tilt by comparison?
23.5.
Beautiful, beautiful. Okay, now, anytime you've got to answer one of these questions, there's usually like multiple subparts. And in my mind, I assign you 5 points on each question based on whether you addressed all the parts. So kind of walking you through how a typical question goes here. They're asking us, does this planet have seasons? Are the planets more or less extreme than Earth? And then always the hard question, which is why? So just, you know, we're going to do most of our homeworks together, so you guys don't have to stress about it too much. But when I'm grading these problems, I'm looking to see, did you address this part? Did you address this part and this part? And sometimes in my mind, I even break down what the 5 points are worth. This is a really easy question. This is your starting question, so we're going gentle on you guys. So, you know, 2 points for if you address whether they have seasons, 2 points to address whether or not there's extreme, and then 1 point for the why. The why is actually the most interesting part, but it's also the hardest, so I kind of go easy on you there. So let's see what you guys remember. I know in our class on Monday, we did a little mini lecture on seasons, and I showed you a couple of flashlights shining down on Earth. It was a little hastily done, but we did it. What do you guys think? Do you expect a planet with a tilt of 35 degrees to have seasons? Yay or nay?
Yes.
Yes, it will have seasons. Extreme, more than Earth or less extreme than Earth?
More.
And here's the big kicker. Tim, can you explain why?
The shift between the angle proportional to the Earth is greater than it is on Earth. So the change is more drastic.
Yes, I like the fact that you said the angle. The angle of what again?
The direct sunlight on each end.
Exactly. So sometimes people say, oh, they start saying the tilt brings you closer to the sun or something like that. It's really about, it's about the angle of the sunlight. Do I have a, here we go. It's about the angle at which the sunlight strikes Earth, right? So for instance, here in this picture of the summer solstice, it's not that the southern hemisphere is closer to the sun. It's that the southern hemisphere being tilted towards the sun has a different relationship between the angle of the sunlight and the planet. With, as we talked about before, the most effective ground rock warming on our planet is being done right about there around the Tropic of Capricorn. So, Tim, you did a fine job with that. Let's just kind of get this down. I want you guys to follow along and write down what I write down, all right? We'll say that a planet with a circular orbit and an axis tilt of 35 degrees will have seasons. Full stop. We expect these seasons to be more extreme than Earth, or than Earth's, I guess, as the 35-degree tilt is greater than Earth's 23.5-degree tilt. So we've gotten our 4 points there. Guys, let me know if you can't read something here. My handwriting isn't what it should be today. And then we'll address the why for that final point. We'll say that this is because so Tim said about the angle of the sunlight. We'll add that it's a variation in the angle of the sunlight. This is because the variation in the angle of the sunlight on the planet, I guess you used the word drastic, and we can use that word, will be more drastic over the course now here I want to say over the course of the year, but of course we don't know if this planet has a period like Earth's, so we'll say over the course of one planetary orbit. And I think that covers us right there. So let me give you guys a minute to write all that down while I sip my tea or my coffee. We're going to need this elixir. Caffeine and sugar are the keys to academic success. So I'm just going to poke around here and look at your faces, see who's writing. Adrian, looks like you might be writing. Destiny, you good? Give me a thumbs up. Okay. Andrew, how you doing? Matthew? Yes. Okay. Yimmercy, you need a second here? Okay. Let me know when you're good.
Are neutron stars really going to have to be redefined?
Tell me about that. Is this something that you saw online?
I did. They found a neutron star that is more massive than the range they predicted.
More massive than 3 solar mass units?
Yeah, I believe so.
What? How did I miss that? Holy shoot. Neutron stars. One of the big topics in astrophysics lately has been that black hole that had a little flare up where they detected a bunch of infrared light, I think, from it. That's been a hot topic, but I have to admit, Tim, I missed that one. Mystery object blurs line between neutron stars and black holes. Oh, actually, I think this is the same article. Holy smokes. All right, I got to look at that. So I don't know if you remember, Tim, but when we took our, where are you guys? I lost you. When we took our 1020 class, sometimes for my 1020 class, I'll have people take a neutron star's mass of around 3 solar mass units, and usually their radii are around 10 kilometers for various reasons. And if you plug it into the escape velocity formula, you get the speed of light, right? So that's amazing to me because I'm not sure how you could have that much mass in that small of a place and still let light escape from you. That's wild. That's so wild. All right, everyone, I'm going to erase this. Make sure whatever you saw, Tim, if you saw that article, send it to me so I'm on my toes when you ask me about it, okay? Sometimes I rely on
I'll
you.
take a look.
Keep me up to date, all right?
Send it.
I wonder if that's, I don't know if this is the, I found an article in Scientific American. I don't know if that's what you saw it, but I'll check it out. All right. Our next problem is chapter 2, number 48. So Matthew, you were the first in the room. How do you feel about reading that out for me? Do you have the questions?
A farther moon.
Good. Sorry. Let me catch up to you.
Yeah.
48, a farther moon. Okay, hit me.
Suppose the distance to the moon were twice its actual value. Would it still be possible to have a total solar eclipse? Why or why not?
So we're pushing the moon twice as far away, and they want to know, simple question, is it still possible to have a total solar eclipse? And then we have to address sort of why or why not. What do you think, Matthew? Can you still have a total solar eclipse if the moon's twice as far away? Let me show you a picture while you're thinking about it here. Oops. Oh shoot, I had this wonderful picture of a total solar eclipse that I lost. Shoot, I had to restart my browser because I was having trouble logging in. Let's see if we can get that real nice. Yeah, this was the web page. I really liked this picture here. So can you see this, Matthew? Are you seeing my screen?
Yes.
All right. So here's the moon. We're going to grab it. Finger of God. We're going to push it twice as far away from the Earth. Can we still have a total solar eclipse? What do you think?
I would say no.
No, you're correct. And how would you describe the why?
Because I would assume that the angular size would stay the same for the sun, but it would go down for the moon.
Beautiful. Dude, I couldn't have said it better myself. My real test in that question was, would you use the phrase angular size? And you did, right? Now I actually have an extensive lecture on eclipses that's kind of fun. And I'm going to deliver that to you, maybe not today, but maybe in our next class. But you guys should understand the concept of angular size, right? If the moon gets farther away from your eyeball, the angle that it subtends is going to decrease. And it would be nice if we could throw in a little detail, like what's the current angular size of the sun and the moon? Do you remember? Does anyone remember the angular size of the moon or sun?
0.5
0.5 of what?
degrees.
Degrees, exactly. All right, we'll add that in for a nice little flourish. If the moon were twice as far from Earth, then no, a total solar eclipse would not be possible. This is because the farther distance would reduce, and here's the key phrase that Matthew was right on point with, the farther distance would reduce the angular size. We'll even underline that. the angular size of the moon from 0.5 degrees. Man, Matthew, wouldn't it be kind of jazzy if we could be technical and actually throw in a number here? Let's see now, if the moon's twice as far away, what do you think? I know I'm putting you on the spot a lot here, but what do you think the angular size, the new angular size would be?
0.25.
Exactly. From 0.5 degrees to 0.25 degrees. And therefore, love to throw in a therefore every now and then. It really sort of glues things together. And therefore, would not cover. Now, here's how an astronomer would talk. It would not cover the full disk of the sun. Sorry, my handwriting is absolutely horrible today. Not cover the full disk of the sun. Now, there's our 5 points right there. We got it. We nailed this thing. But suppose we wanted to just, you know, add like a little extra, just because we can. What type of an eclipse would be possible if the angular size of the moon was 0.25 degrees?
An annular eclipse?
Yes. Instead, you get an annular eclipse. And that's nice because then we convey to the reader that other types of eclipses are possible. Annular eclipse. What am I doing? All right. I'm gonna get out the Windex and I'm gonna clean up my boards to try to improve my handwriting. Okay, sorry, it took me a minute to find this thing. How are we doing? Do we have everything we need, students? Anyone who needs extra time, or do you have it all down? Looks like everyone's cool. Give me the thumbs up. All right, give me a second here. I'm just gonna do this right. Ooh. Hopefully you guys have the numbers written down because I just Windexed them. Believe it or not, this is important because the dirty dry erase board destroys your markers. And now that I'm paying for them, it's real. You know what I'm saying? They used to just appear in front of my face. Someone used to do all this for me. I'm doing it myself now. It's much less fun. So we want to preserve those little puppies. Yes, we do. Okay, let's find another victim to read me a problem here. Yimmersey, what do you think? You want to give it a whack? What's our next problem?
Our next problem is 53.
So oh, by the way, guys, I know you're all new to the game. Some of our homeworks, some of our homeworks sometimes span multiple chapters. So I just get in the habit of putting chapter 2.53 in front of everything. That helps the reader, me, understand what's going on. Sometimes ain't too bright. You want to make it really obvious for me, okay? All right, so Yimmersy, what's the title of this little problem?
Arc minutes and arc seconds.
Beautiful. Okay. I think we talked about this really briefly. I sure hope we did. All right. Let her rip.
All right, do you want me to read it now?
Yes, please.
Okay, there are 360 degrees in a full circle. A, how many arc minutes are in a full circle?
Okay, let's stop there. It's very important. This is probably obvious to everyone, but just because I've seen otherwise, if there's an ABC part, we have to label it real careful. That lets me follow what you're thinking and doing, okay? What I can't remember, because I've taught a lecture yesterday since seeing you guys, did we get into the arc minutes and arc seconds it probably came at the very end of our class, or did I not cover it all? Yeah, Tim, we did do that?
Yeah, we did.
We at least, hopefully we at least slapped up those conversion factors, right? Well, this is a problem about conversions and dimensional analysis. And what I should have told you guys is that 1 degree contains 60 arc minutes. You guys might want to remember that the single apostrophe is our symbol for arc minute. Let's put that in a box in the upper corner. And 1 arc minute, which is itself already a tiny angle, can be further subdivided up into 60 arc seconds, which is indeed a very tiny angle. So Yimmersy, while I've got you in the hot seat, what are we going to do?
So if let's see. You will have to try to find the diameter.
Oh, no. It's much simpler than that. Yimmersy, this is a problem that can be entirely solved using dimensional analysis. And what's cool about dimensional analysis is you can kind of switch your brain off and follow the steps, and it naturally guides you through the problem. So why don't you go into your notebook if you have it with you, and I should have put a big smiley face next to the 4 steps of dimensional analysis, and I want you to just read them back to me, and we'll do this one by the numbers, as they say.
All right, so we will have to try to figure out what numbers to put in first for the scale factor.
Read it verbatim, right from step 1. What's step 1 tell us to do?
And you said the big smiley face, right?
I think so. I mean, I remember having 4 steps of dimensional analysis, and sometimes I put a star next to it, sometimes I put a smiley face. But Yimmersy, I need to get you new students to memorize these steps. That's what I need from you. So reading them back to me is going to be our first step of collective memorization. So did you find it in your notes?
I think I got number 2.
You didn't get number 1? Does anyone out there have number 1? You better write this down, Yimmersy. This is going to be important in your life. Megan, Janabelle, Adrian, Andrew, have any of you guys got them steps written down? That was kind of a big deal for me. All right, Adrian, hit us one time.
Here we go. Number 1 is write down the numbers to convert with units.
All right, so that gives us something to think about. What the hell are we trying to convert here? Adrian, do you know?
The 360 degrees.
So I guess we should start there. Hey, Yimmersy, if you like were trailing behind in the notes and you missed this, I want you to write down those words verbatim, squeeze them in your notes there. Yep. Write down the number to convert with its units. Just like that, okay? And Adrian's saying, hey, we got to convert 360 degrees, so let's start by writing that down. All right, Yimmersy, what's step 2 since you got that one?
Multiply by division bar.
Easy peasy pie. Boom. How about step 3?
Split unit and cancel.
Put the units in first. Units first. That's the idea.
Okay.
So let me have a statement of the problem here, Yimmercy. You are currently rocking the degrees, but you don't want the degrees, you want arc minutes. I need you to give me a unit on top and a unit on bottom. Do you know what to do here?
You will put 1.
No. You don't touch
cancel it?
any numbers. This
Okay.
is the psychic idea. You don't mess around with any numbers. It's units only.
Okay.
So do you know which units to put on the top and on the bottom?
No, I do not.
Okay, that's fine. This is your first time through the gate here. How about, I know Tim knows, so Tim is probably, he probably went back to bed on us here because Tim's had this drilled into his brain by me. How about the rest of you guys? Do you know what units to put in? Adrian, hit it.
Put degrees on the bottom and arc minutes on the top.
Yeah. So let me talk to Yimmercy for a second. Hey, Yimmercy, the idea is whatever units that you have, you probably don't want them anymore. Otherwise, you wouldn't be playing this game. So if I have degrees, I recognize them as being on the top, and I match the same unit degrees on the bottom. So that's the easy part. You always know that whatever you have up here, you put the same unit down there. Up here is what you want to convert into, which is arc minutes. Okay. And now step 4.
Split unit and cancel.
Well, the unit. Oh, by the way, why don't we do this? Let's cancel out the units to remind ourselves why we do what we do. Now degrees are canceled. But what about step 4, Yimmercy? Do you have step 4?
You're gonna split the number.
You put the numbers in second using your conversion factors. So Yimmercy, this is your conversion factor up here. 1 degree is equal to 60 minutes of arc. So you want to take a guess as to where the numbers go? I need a number on top and I need a number on bottom.
Okay, so the 1 is on the bottom, 60 is on top.
That's right. Because it's 1 degree equal to 60 minutes of arc. So Yimmercy, you know, in general, taking notes is your own private concern, and you guys can take them however you like to do it. But for the 4 steps of dimensional analysis, I want you to think about them like Moses' tablets, okay? These are the word of the Lord. You don't want to mess with that. You want to get those words written down exactly as such in your notebooks. And it may be that I went a little fast or something, but Yimmercy, make sure that you have written down, you put the numbers in second using your conversion factors, okay? Oh, hey, how many of you have your bloody Casio today? Let's see who did better. I got mine. Yeah. Andrew, take that thing out of the package. Destiny, I like it. Oh, Adrian, oh, Nick, I forgot that you were trolling us in the shadows there. We got a perfect Hollywood squares, Nick. We wouldn't even want to see your face. Okay, so, all right, Nick, I'm glad you got the calculator. Adrian, you're going to use your fancy one. Fine. Hey, Adrian, do you know how to take a 4th root?
I forget how, but
Casio.
I remember kind of being told when I took trigonometry, I think.
Look, I can help you how to do that when the time comes. Oh, Staples lied to me. Oh, Nick doesn't have a camera. Okay, Nick, we're just messing. I'm messing with you. Okay. Nick, I'm glad you're here and I'm glad you got that Casio. Adrian, that's fine. We can use your calculator, but Adrian, it's $9. And I want to tell you a story because in case you are trained in some of the Jedi arts of physics or something like that, I had this awesome tutor. He was like one of my best tutors. And he had one of those big old honking TI-85s. I've got one somewhere back here on my shelf. And I trained him, I forced him, once he started tutoring, to use this thing, right? And he ended up going on to Worcester Polytech to study aerospace engineering. And when he came back, you know, one day he calls me back up and says, hey, B, let's go get a drink at a bar. I'll tell you about what it's like at Worcester Polytech. And what he wanted to talk to me about was the fact that he was sitting there competing with all these engineers who were rocking their big calculators. And he said, it was amazing. I could just out-calculate them all because I was so fast at this. It was like my hip shooter, you know? And they were all sitting there lumbering through their calculations, and I was doing trick shots and flipping this thing, and everyone was like, man, how'd you get those calculator skills, you know? So, Adrian, this ain't about keeping it easy. This is about keeping it cool, all right? So this calculator is very powerful. But anyways, I like the big ones too. They're nice for the graphing. Consider joining Team Casio. Guys, all you got to do is multiply 360 by 60. What do you get? Punch it in. Okay, so Janabelle, what do you think? How do we say that? You got it right, Janabelle. So what do I write down?
You write down 2 point.
No. No scientific notation is needed today because that number is less than 1 million.
Okay, so 21,600.
Yeah. And what are the units?
The units are.
All you got to do is look up here to see what's left over. Degrees have killed off degrees, leaving you, what are those things called again? What are those things called again?
Arc. I'm not sure.
Arc minutes.
Arc minutes. Okay.
Arc minutes, which we use with a single apostrophe, right? Learning to use these terms and talk about them is part of your training. By the way, just in case an advanced student out there is wondering about precision, I get to keep all of those digits, don't I? Tim, I wonder if you understand why, because sometimes I like to pick on the 1020 veterans to see what they've learned. Tim, do you know why I get to keep all the 2216 in my 21,600?
Because arc minutes are more precision than degrees. You're trying to get more precision from them.
I don't know if I like the sound of that. It's about precision, and it's about the precision inherent in arc minutes. But arc minutes are not more precise than degrees. We could not say that. What we could say is that by definition, there are exactly 60 arc minutes in exactly 1 degree. Those numbers have infinite precision baked in. And one easy way to see that, Tim, is if you imagine a circle. You may have learned in some ye old geometry class that the radius of a circle is half of the diameter. That half is not a measurement, but it is a conceptual 1/2. It is exactly half of the diameter of the circle, correct? You know what I mean by that, right? So these are conceptually infinitely precise. I wanted to throw that out there because I talked about precision at the end of lab. Okay, who is reading for me? Let's get on with this bloody thing. Yimmersy, were you reading us part B?
Yeah. Yes, part B. How many arc seconds are in a full circle?
I can think of a couple of different ways to do this. There's 2 ways to skin this cat. Megan, what do you think? How should I go about this?
I was thinking that you would multiply the 21,600 by 60.
Okay, right. But suppose I wanted to like make it dimensional analysis style. Like everything you said is correct.
Okay.
Let's start with our 21,600 arc minutes. Let's go through our steps of dimensional analysis and just do it all right proper. So what do I do next?
Times
the division bar. That's step 2.
Sure. Times on the bottom, it would be, I'm not sure, I'm sorry.
No, you can do it. Do you have your steps of dimensional analysis?
Of course.
The funny thing is, Megan, you already know how to solve this problem, right? But I'm making it more complicated for you, and for good reason, okay? So what's the 3rd step in dimensional analysis? Just read that off the page.
Sure. The 3rd step is to put units in first to cancel out. So on the bottom, the denominator, it would be arc minutes.
Okay, and on the top?
It would be arc seconds.
Okay, and a sort of double quotation there is for arc seconds. Okay, and what's the step 4?
Step 4 is to put numbers in second using conversion factors.
You got a conversion factor in your back pocket. I need a number top and a number bottom.
Okay, so 60 on the top and 1 on the bottom.
Now, if I were you, I might be asking myself, I already knew how to solve this, dude. Why are you messing with me, right? It's because we're going to go to a place. We're going to go to a place that's more complicated than this, and it's going to become more disorienting. These steps will keep your mind clear, right? So let's cancel out our arc minutes and multiply them up and tell me what you get, Megan, on your Casio there.
1,296,000.
Oh, wait, there was a rule about scientific notation, right?
Yes.
Numbers. All right. So help me put that in a scientific notation.
Okay. So it would be 1.3.
In this case, so this is what I was riffing with Tim or someone about. You actually get to keep those numbers, Megan, because these conversion factors are infinitely precise.
Oh.
Now, if you had rounded it to 1.3, it wouldn't exactly be wrong. I would forgive you. But because I'm trying to teach you stuff today, I want you to know that all of those numbers are meaningful. We're going to keep them all. 1.1.
1.29.
Is there anything else? Is it 296?
Yes.
Keep it all. It all matters.
Mm-hmm.
1.296. Yep.
Times 10 to the third.
Beautiful. Oh, no, no, not beautiful. Here, let me do this. This is what you're seeing, right?
Yeah.
So let's remember how we do this. We got to move that decimal point, right? But
Yeah.
a bink. Want to try again?
To the 6th.
Yeah. 1,000,000 is 10 to the 6th.
Yeah.
And now that's arc seconds, so I'm going to put units up there. Don't make that look like 611, my sloppy handwriting friends. Make sure that I understand that it's 10 to the 6 arc seconds. Put a box around it because that's a classy move. All right. Nice. Okay. So there, Megan, we employed our rule, which is if it's more than 1,000,000, scientific notation. Normally, your instinct to round would have been correct, but today we get to keep a few extra digits because it's a perfect conversion. Okay, Yimmersi, you want to get us down to part C?
The moon's angular size is about 1/2 degrees. What is the arc minutes in arc seconds?
So we want to convert this to both arc minutes and arc seconds. Andrew, you're next on my Price is Right. So why don't you tell me what I should do here? Because I'm starting to feel confused.
Would you take the 1.296?
No. This is a new problem, new day. Why don't you look at do you have your steps of dimensional analysis written down?
Yeah.
So why don't you take me by the numbers through those steps?
Write down the number to convert with its units.
So what number should I write down with its units?
0.5
degrees.
degrees.
Yes. Fine. Okay, what's the second step?
Multiply by a division bar.
I can do that. What's our third step?
Put the units in first to make them cancel out.
All right, give me some units, top and bottom.
Degrees would be on bottom.
Yep.
And
now we have to ask ourselves, what the hell are we trying to do? What are we trying to convert it into?
I'm going to pull up the question too.
Yes, that can be helpful. Sometimes it talks a dang much, you forget the damn question.
Arc minutes.
Yes. And step 4?
Put the numbers in second using conversion factors.
Well, I think I see a couple up here, son. So give me a number on top and give me a number on bottom.
1 degree.
Pardon?
1 degree.
Where do I
On the
put the
bottom.
1?
On the bottom.
Yep.
and then 60 on top.
Fine. Hey, can you do that one in your head? If not, use your Casio, I guess, but I could do that one in my head.
V30.
Yeah. Arc minutes, he says. Now that's half of part C. We also have to find the number of arc seconds. So if I was going to use Megan's logic, which is pretty good, I should start with what I've already done. That's how we did it up there. Start with the 30 arc minutes. And let me grab another person. Destiny. Destiny, I know you're sitting a little far away here, but talk to me so I don't get lonely. What should I do, Destiny?
Okay, so you would do 30 arc minutes.
Got it? And now let's do step 2 of dimensional analysis. What's step 2?
You multiply by the division bar.
That's easy enough. Step 3 is the units. So I need you to give me some units, top and bottom.
So at the top, you do arc seconds, and at the bottom, arc minutes.
Beautiful. Couldn't have said it better myself. And step 4 is the conversion, the numbers, putting in the numbers.
Mm-hmm. Yeah, so 60 at the top and 1 at the bottom.
Beautiful. All right, so punch them up or do it in your head, whatever you do. Tell me what I got.
1,800 arc seconds.
Beautiful. Just like downtown, but closer. And that wraps up problem 53. We're moving right along here. Today's homework isn't too bad. I think there's kind of a nasty one at the end, but we'll get to that. So I'm just going to leave that up there for a second, make sure you all got it. Okay. I'm just poking around your faces, and it looks like everyone's got the stuff as far as I can tell. Andrew, how are you doing? You good? Yep. Okay. Cool. All right. Adrian, you good? You got everything down? Okay. All right. Sometimes in the past I've erased too quickly, so I'm trying to not do that. Here I go. I'm erasing. All right. Adrian, while I've got your ear, what's the next number?
Number 27. 57. Sorry.
57. That sounds good. Okay. And what's the title?
Sun diameter.
Okay, read it out to me.
Use the sun's approximate distance of 150 million kilometers and angular diameter of about 0.5 degrees to calculate the sun's physical diameter. Compare your answer to the actual value of 1,390,000 kilometers.
1,390,000 kilometers. How would I put that into scientific notation?
1.39 times 10 to the 6th power.
Good. All right. So this is kind of weird. They already gave us the answer, but they want us to find the answer anyways. That's actually very normal. That's a very normal thing to do in science, is to see if you can get the answer if you already suspect what it is. Now, we need a formula to do this, Adrian. Do you remember what the formula was? Did I even give that formula to you? I can't remember what the hell I did.
You likely did. I just need to.
It would have been at the very end of lecture, and I would have put a box around it because it would have been important. But I was doing the end parts a little hastily.
There was one section you wanted us to remind you that you needed to cover today that you didn't finish. I don't know if that was it, though.
Man, my memory is that it was the arc minutes and the arc seconds. I wanted to talk more about them. Normally, I try to make you feel the angles and not just give you the definitions.
You did use the small angle formula yesterday.
All right, okay, that's what we want. So Tim, why don't you remind us how it goes? If you
Size,
Uh-huh.
S, equals the angle times the distance times 2 pi over 360 degrees.
Beautiful. All right. So class, the only real thing you have to do in this problem, normally there's some unit conversions that happen first, but in this case, our units are actually pretty good. We recognize that 0.5 degrees is our angle. We recognize that 150 million kilometers is our distance. And that means we're kind of pretty much ready to go. We just got to plug them in and chug them in. So we'll write it again. S equals 0.5 degrees times 150 million kilometers. And then we're going to go times 2 times pi divided by 360 degrees. Now, this is pretty easy as far as it goes, but for you guys who are learning and are new to the game, the trick is to make sure that you punch it all in one clean shot, just like you'd cut the head off a snake, one stroke, okay? So don't do it all piecemeal. We're going to punch together in the Church of Casio here, okay? So we'll do 0.5 times 150 exp 6 times 2 times, to activate pi, simply hit exp and then divide by 360 and equals. So Janabel, do you got something on your machine there? What do you got?
It looks pretty crazy, but
Okay. Yep. The first time around it does. You have the right number. I know that. My goal is to get you to tell it to me. Okay. So let's ask us a couple of questions here. Is that number greater than 1 million? Yes or no?
yes.
Then we got to put the answer in scientific notation because that's a rule. So why don't you start nice and easy? What's our lead digit?
1.
Okay. Now, how many digits do you think we should keep after that?
1 more.
Normally, one more would be the answer, but here something's going on, Janabel. We have to compare it to the book's value. And can you see that they included 3 sig figs in the book value? We should also do the same because when you compare two numbers, you want to force them to have the same precision. It doesn't do any good to compare 0.5 to 0.5296734. You know what I'm saying?
Yeah.
So give me 2 digits after.
Okay. So 1.31.
Exactly, because the 8 rounds the 0 up to 1. So that was another test to see if you'd round proper, and you did. Times 10 to what power?
Times 1, 2, 3, 4. To the 5th power?
Hold on, let's try that again.
Am I wrong? 1, 2, 3, 4, 5, 6. Sorry.
Yeah. So the decimal place is there. This is for everyone else too. 1, 2, 3, 4, 5, 6. 6 times. And what are your units?
Arc minutes.
No. To find the units, you look into the formula, and first you cancel out any units that can be canceled out. For instance, Janabel, I notice that there's a degree on the top, and down here there's a degree on the bottom, and that means these guys cancel out. And that only leaves 1 unit left over. What's that?
Is the arc seconds? I'm not sure, honestly.
That's okay. All right. So this is us learning how to talk to each other. So Janabel, not every number in this equation has units. 0.5 has units of degrees.
Okay.
And the degrees have canceled with the 360.
Mm-hmm.
2 is just a stupid number. That doesn't have units.
Okay.
Pi doesn't have units. But 150 million does have units, and the units are?
Look at the question.
Do you know what those are here? What's the km mean?
Kilometers.
That's right. And since kilometers did not cancel, it's got to be left behind. That's your unit.
Okay, so it's 1.31 times 10 to the 6th power kilometers.
Yes, there you go. And this is a game we're not going to just play once. We're going to play this a bunch of times. We look through our formula, we see what cancels, and whatever's behind are our units. Let's put a box around it because that's a classy move. At this point, you might think that we are done, and you would be wrong. This is why we need to do our homework together so that you understand what a scientist wants from you. When we read the problem, Adrian, I think, read the problem. It asked us to calculate the diameter of the sun, and we've done that, 1.31 million kilometers. But it asked us to do something else. Adrian, what did it ask us to do?
It asked us to compare it to the actual answer.
Yeah. Now, if I was a student and this was my first rodeo, compare to me might mean all manner of things. It might mean, hey, look at my number and look at the book's number. They're not the same, right? That's kind of interesting. Nope, that's not how we do it. Another thought that I might have is to subtract and ask about the difference. But I'm going to tell you something, guys. Subtraction is for zeros. In astronomy, compare means one thing and one thing only. Take the ratio. That's such an important idea that we're going to write it down. Compare. That means something to me, to a science person. It means take the ratio. Now, there's a couple of different ways you can take the ratio. You can divide the big guy by the little guy. That tells you how many times bigger. But when the numbers are kind of close, as they are today, I like to divide the little guy by the big guy when the numbers are close so I can see what percentage they are from each other, right? So, in other words, I'm going to divide the size of the sun that I calculated by the size of the book value. And on the top, I'll have 1.31 million kilometers. On the bottom, I'll have 1.39 million kilometers. So I want you guys to punch them up. Punch them up in your calculator, please. And then I want to talk to, oh, I don't know, any one of you guys. Megan, let's talk to you.
Okay.
So tell me what you see in your calculator.
I see 0.94244043.
All right, let's not get carried away here. First of all, when we write down numbers that are less than 1, my friends, always put the leading 0 out front. And that's because not everyone's good with the handwriting, and sometimes you're quick and sloppy. Decimal points are harder to notice. So 0 point, I'm going to recommend 2 sig figs, Megan, and that's not a sig fig. So what are we going to keep if you're going to keep 2 sig figs?
94
Okay. What are the units of this 0.94?
kilometers.
No, it is not kilometers because there's a kilometer on top and a kilometer on the bottom, and they just canceled out.
Oh, yeah.
So what does this 0.94 mean? I'm scratching my noodle trying to figure it out. What's the 0.94 mean? Anyone out there in TV land know what 0.94 means?
Doesn't it not have any units?
It doesn't have units, but that doesn't mean it doesn't have meaning. Hey, Adrian, suppose you and I had like a cookie bake-off, right? And suppose that I bake 5 cookies. And suppose that you bake 10 cookies. And then the book were to ask us to compare your cookies to my cookies. We would divide 5 cookies by 10 cookies. The cookies would cancel. And I'd end up with 0.5. What would the meaning of the 0.5 in that case be, Adrian?
That's the comparison of your number to mine.
Right, but how do I say this in an elegant way? 0.5, what's the meaning of the 0.5? maybe I'm being too vague. Does anyone understand what I'm getting at here?
Percent?
Yeah, so Tim, this may be that you've hung out with me too long and now your brain is infected with my ideas, but whenever I see a number that's between 0 and 1, my instinct is to think about it as a percent. So in the case of the cookies, what it would mean, Adrian, is that I have 50% of the cookies that you have. I have half as many cookies, right? So by analogy, this would be 0.94 would mean what?
So 94%.
Of the book value, right? And we can write that down as part of our final answer. Okay, so those were some learning lessons. We got one more problem to go, and we have more than half an hour. By the way, I understand that doing this can, even when you're just kind of following along, it can be taxing. So I try to build in an extra little break between our office hour session and our lecture. That just gives you time to chill. But we got one more problem to go before we can do that, and this problem is a little bit of a whopper. So I don't know, who haven't I bugged yet? Matthew, let's go back to you for fun. Matthew, can you read us the last problem? Wait, hold on. Does everyone have this down before I erase? Anyone need an extra second here? Adrian, you good? Okay. So Matthew, I'm gonna bug you to read again for me.
Okay.
What's the number?
59.
And what's the title?
Eclipse conditions.
Actually, before you get going here, I'm going to give you like a little preamble to this problem because it's a little bit more work than the last 4 that we did. We're going to have to rearrange the small angle formula, and I want to do that on your page before we get going. Remember, students, not only are you doing your homework right now, but you're building up a super sick study guide for the scary test that you're eventually going to have to take. And this is stuff that you're going to want to look at later. So we have this small angle formula. The size of our sun, or the size of our moon, is the angular size times the distance times 2 pi over 360 degrees. Now, in this problem, in this variation of the problem, they're going to want us to calculate the angular size and compare the angular size of the sun and the moon based on the fact that their orbits are not perfectly circular. So we got to do a little algebra here. That's not everyone's favorite thing. Notice that my angle theta is on the top right now. I'm going to leave it alone, and I'm going to flip everything over to the other side. So if you can flip a burger, you can flip an equation. The trick is to not be afraid to solve for a variable on the right-hand side, okay? So what I'm going to have is, if I drop the d down, I'm going to have s divided by d, all right? The d crosses the equal sign and has to go to the bottom. The 360 will go up to the top. And the 2 pi will drop down to the bottom. So I just did that. I just did me some algebra by flipping some numbers around. But I did it in a funky way where I kind of solved for theta on the right-hand side. Now, the only other rule is I can flip everything at once, and then I can keep everything in the same spot. So this becomes a formula for angular size. I almost hate to call it something new because it's still the small angle formula. It's still that formula. But because we're using it in a different way, and you guys are kind of new to the game, we're going to give it its own name. This is the formula for angular size. Theta, the angular size, is 360 degrees over 2 pi times the size divided by the distance. Now, you're not going to use this formula once or twice with me. You're going to use this formula a whole lot. So it almost makes sense to kind of put a box around it and make a deal out of it. And that's the formula that we need for our problem today. So Matthew, now we can read.
So The moon's precise equatorial diameter is 3,476 kilometers, and its orbital distance from Earth varies between 356,400 and 406,700 kilometers. The sun's diameter is 1 million.
Sorry, Matthew. Give me a second. You might want a second too. The thing that he's reading off right now, these are called the givens in a tricky problem. And I found it's a good idea to get the givens down on the page. Now you were reading, so you want to take a second there to get those numbers down? And when you're ready, when you've got your givens down, Matthew, read us the sun bits.
All right. So the sun's diameter is 1,390,000 kilometers. And its distance from Earth ranges between 147.5 and 152.6 million kilometers.
I'm going to translate million right into 10 to the power of 6 because I'm good like that. I'm not afraid of numbers, right? I'm just going to put them down. 10 to the 6 kilometers. 10 to the 6 kilometers. All right, cool. And now what the hell do they want us to do?
All right, so A is find the moon's angular size at its minimum and maximum distances from Earth.
The trick to this problem is to stay organized and make sure that our top-down structure is readable. Notice that I've labeled that we're doing this for the moon. First thing I'm going to do, did they say min and max or max and min? What was the order they said?
Min then max.
So let's do min distance first, okay? We're going to bust out our angular size formula, okay? So we have theta equals, now, Matthew, what do you think we should put in for S and D here? Have you been following this?
Yeah. Sorry, I'm still writing down.
Oh, sure. Take a second.
Yeah. Right. So the S would be 3,476.
That's our diameter. Kilometers, of course, you meant, right?
Yes.
And then what about for our minimum distance?
That'd be 356,400 kilometers.
All right. It's almost time for some punching. Now listen, I already know some things that y'all don't know. I know, for instance, that you're about to screw this up, all right? So you're gonna have to pay very close attention to what goes down here because there's only 1, 2, 3, 4, 5 numbers, but it's very easy to botch this. What I'm particularly worried about is the pi here because I know some of you were gonna try to do 360 divided by 2 times pi, and the people who are doing it even worse are going to type 360 divided by 2 pi. Never use implied multiplication in your calculator. You got to tell it everything you're doing. Also, when it comes time for this guy, we are going to divide to let the damn calculator know that pi should be on the bottom as well. So let me show you how I punch this, and you just follow along and you'll learn, okay? Let's start with 360. Adrian, the rules apply for you as well. Divide by 2, then divide by pi. Adrian, you have a pi key there somewhere. You might know where it is. Now we'll go back to times to get back up on top. Times 3476. Divide by 356,400. And then equals. Adrian, since you're, since you're using a funny calculator, I want to hear about what you got on your screen. And then Janabel, I want to hear about your number too. Let's start, Adrian. When you've punched it in, what do you got?
This does not look, well, 0.5588 106891.
That's good. Are you seeing the same thing, Jennifer?
Yes,
You're
I am.
all right, good. Now, Adrian, that number is perfectly good. There's nothing wrong with that number. Adrian, I'm not done with you. I'm going to ask you a very adult question here. How many significant figures can I keep here? Significant figures are about the precision of your measurements. Where are the measurements in this equation?
4.
Yeah. Notice that you've got 4 digits of goodness on top, and weirdly, you've also got 4 digits of goodness on the bottom, meaning you can keep 4 digits of goodness. So what should I round this to then? Or yeah, what should I write down?
0. Well, do you want me to put it in scientific notation?
Hell no. I can handle 0.5s.
So 0.5588.
Yeah. The 0 doesn't count. So 0.5588. And what are my units?
Degrees.
Yeah. Kilometers cancel out, so degrees are all that's left. Box it up. All right, now let's do the max distance. Theta equals 360 degrees over 2 pi. The diameter is still the same, 3476 kilometers, divided by the big distance, 406,700 kilometers. This one you guys do on your own. Punch them up, and Destiny, maybe you can tell me what you get. Destiny, you got a number for me?
Yeah, do you want the final or do you want what I have right here?
I just want the final thing properly rounded. You're gonna keep 4 sig figs again, right?
Yes.
All right, so just give me this version.
Okay, that's 0.4896.
But you just chopped a 9, didn't you?
Yeah.
You chopping 9s on me, so maybe it would be better to do what?
Round it?
Yeah.
Okay.
So what should I write then?
0.4897.
Yeah. The units?
Degree.
Good. If you're going to cut the number, you got to round it. Round it right proper, which you have done. All right. That's the moon. Now, Matthew, I think they want us to do the same thing for the sun, don't they?
Yes.
Okay. I'm going to be a little lazy. I'm going to cheese ball out on you guys here. I'm going to save myself some marker time, and I'm going to relabel this B. I'm going to relabel this as the sun. You guys are going to have to write it all out again, obviously. But I'm going to swap out my numbers here because I'm having that kind of a day. Actually, so I want to try to do this all in one shot so I can get a little tea break in before class starts. So the diameter is 1.39 million kilometers. And that'll be the same for both problems. For the sun's minimum distance, I'll have 147.5 million kilometers. And the max distance will be, oops, 152.6 million kilometers. I hope you guys can read that. That was a little squishy of me. Let me know if you can't read that stuff. It looks clear on my screen, but I don't know how it's translating over the internet.
Is there any way you can just make it a little bit closer?
Yeah, actually, what if I write bigger? That would actually be better. Is it the bottom stuff or is it everything?
Yeah, just the bottom stuff.
Yeah. Whoa. How about them apples? Okay, guys, look, once you got it written down, punch them up. I want to call on random peoples and hear some cool numbers. You got that, Janabelle? All right. Tim, we got to show you some love too. You got that first one for us?
It's 0.54 degrees.
I'm gonna 2 sig figs is de rigueur, but I'm still teaching you all about precision. So how many sig figs do you get to keep in this one, Tim?
Shouldn't it be 3 because 1.39 is only 3?
Yes, sir. So what do you want to round that to then?
0.5.
No.
No.
Oh, I'm sorry. I'm sorry. I didn't punch it in. Hold on. Let me just.
You have to round it.
Yeah, but hold on. You're probably right, but let me just. Okay, sorry. What do you want to round it to?
0.54 degrees.
I would make one correction. 0.54 is still 2 sig figs. How do I make that explicitly 3 sig figs, Tim?
0.540.
That's right. That tells me that the 0 is meaningful. So 0.540 degrees. There's a difference to my thinking between 0.54 and 0.540. 0.540 means it's 0.54 all the way up to the next line, you know? All right, how about the bottom? Someone want to punch up the bottom for me? Andrew, you floating around there somewhere?
Yeah, I'm trying it right now.
Give that a shot. I want to make sure you can handle this. You got to do 360 divided by 2 divided by pi times 1.39 exp6 divided by 152 exp6. And then equals.
I think I messed up.
All right, well, do it right. Where are you messing up?
It just does not.
All right, you got your Casio?
Yeah.
You watch me, and I ain't just talking to Matthew now. I'm talking to any of you other slackers out there that might have missed the instructions in this, okay? You follow me. You do what I do if you want to learn, okay? So let me kind of get out of the way here. So we'll start. Follow me, Andrew. 360, all right? Divide by 2. Divide by pi, which is exp, times 1.39 exp6 divide by 152.6 exp6, and then you hit your big old equal and you tell me what you got.
Okay, that's what I did wrong. I got 0.521 8,
But
and then the 9 would bump up the 8 to a 9.
hold on. I want to talk to you about a thing that me and Tim were discussing.
Okay.
This problem, we can only keep 3 sig figs because the sun's precision is limited to 3 sig figs. So
This
that
is a 3.
proves the answer. How would I round that to 3 sig figs?
It'd be 0.521.
But you just chopped an 8, didn't you?
Oh,
So try again.
that'd be 0.522
Yep. And what are the units?
degrees.
Yep. All right. Get her done. Get all that down. We almost done with this. Who was I talking to? Matthew. What's part C ask?
Based on your answers to parts A and B, is it possible to have a total solar eclipse when the moon and sun are both at their maximum distance? Explain.
Let's try to see the big picture here, Matthew. At the max distance, the sun had an angular size of 0.5, we'll just call it 0.52 degrees for simplicity. What was the moon's angular size at max distance? Rounded to 2 sig figs.
Were you asking me?
Sure.
Okay. 0.49 degrees.
So does that look like we're going to get a total solar eclipse here? What are you thinking? Matthew, what do you think?
No.
No. And why not? Because you had the cool answer for that other question. This is kind of like the other question all over again.
Because the angular size is smaller.
Yeah. And Matthew, I think you're seeing it because you've got that answer before. But let's just do this here for anyone. Here's the sun, right? And then we'll draw the angular size of the moon. Here's the moon. I'll kind of shade that in. And we've got 2 different, let's pretend like this is an architectural drawing here, right? This is, the moon's angular size is 0.49 degrees, whereas the sun's angular size is 0.52 degrees. What type of an eclipse is that, Matthew?
I'm guessing from before it's an annular.
Yeah, exactly. This is how annular eclipses come about. If the moon and sun happen to line up when they're at their, we call it aphelion for the sun, we call it apogee for the moon. Let's write some words. No, a total solar eclipse is not possible at the maximum distances, because there's 2 distances, because here we can be a lot more technical than we were in the third problem. I like this problem because it's basically the third problem, but it's just way more in depth. Because the angular size of the moon, I'm going to abbreviate. I like being technical. It's 0.03 degrees. Doesn't seem like a lot. But your eyeball can see that, my friends. 0.03 degrees smaller than the disk of the sun. Instead, you get an annular eclipse. Well, the church bells are ringing, but it's 10 of. Maybe it's time for people to go to church or something. Okay. So guys, that'll give us a little mini break before lecture starts. That concludes homework number 1. Congratulations, you got it done. And you guys want to take a little mini pause before we get back into the lecture? I'm sure that would be nice for y'all. By the way, I did not grade your lab. I was a bad boy last night and I didn't do anything. Well, I didn't do anything good, let's put it that way. So I will grade your labs at least by this weekend. So sit tight on that. Everyone did submit their lab, correct? All right,
Yes.
good.
Well, are we doing the same thing with our homework? Are we uploading them?
Yeah, and if you want to just get her done now,
Yeah.
or if you need your little break, take that, whatever. But it's not that it has to be done right now. I just don't want you guys to forget. So I'm sharing my screen there just for anyone who might have missed yesterday. You go to homework 1, you click it, and you browse here and upload just take a scan or a photo of it. By the way, I did figure out some things. Make sure that you got your high dynamic range off when you take that photo. You want the photo size to be small. When the photo size is too large, it makes it an attachment rather than a little preview box. But whatever, just submit it. And I'll tell you what, at the end of class today, when you submit the labs, we'll look at everyone's stuff. We'll see who's been naughty and who's been nice, all right? So submit that. Maybe give ourselves to 5 past 12. Give ourselves a good 15 minutes to have a little snack, okay?
I have a quick question.
Oh, yeah.
So the first lab, there were some tables sets that we didn't do together.
Don't worry about them.
Oh,
Just
okay.
that. I had to chop some stuff off that lab so that I could blab a little bit. So
Okay.
I think we just ended up doing 1 page, and I'm totally cool with that. Just submit the 1 page you worked on, okay? Yep, awesome. All right. So I'm gonna mute myself, but I'll be here in the kitchen having a snack. So give yourself a good 15 minutes to chill out. Tim, I had myself a little breakfast snack, and I read the Scientific American article about that neutron star. It's pretty interesting.
I put a link in the chat.
Oh, good.
I'm
Yeah,
not sure which journal it originally came from, but I saw the article on BBC News.
Yeah, usually when they get to when they percolate up to the news, it's usually the most prestigious journals are Science or Nature. So the journalists love to digest those papers. Although it's possible the sort of gold standard for astronomy is the Astrophysical Journal. So it's funny, I didn't get far enough into it to see which one it was, but it started off as a gravitational wave detection, which we did not quite get to in your class, but the curvature of space-time can have these ripples in it. Basically, it's like electromagnetic radiation, except instead of oscillating the electromagnetic field, you're oscillating a gravitational field. And this amazing LIGO detector, they have one in, I believe, Virginia, one in Washington. There are these really long lasers where it's like a 4-kilometer track, and they keep a careful measurement of the length of the laser down to like the diameter of a proton. It's one of the most high precision experiments ever done. I think the precision is 1 part in 10 to the power of 24. There is no human creation that has a higher precision than this. And they just use interferometry to get very, very precise measurements of the length of this laser. So when the gravitational waves pass through Earth, they cause a small oscillation in the length of the laser, like a really tiny one, and they measure it. And because they have 2 stations, one in Virginia and one in Washington, they can tell the direction, the rough direction of the gravitational wave and try to pinpoint where it's coming from. So I won't get into all of it, but weirdly, like if a neutron star merges with a black hole, the asymmetry of the 2 objects is what really produces strong gravitational radiation. So the signal they got told them that it had to be a neutron star black hole merger. But what was messed up is normally over around 2.5 solar masses, neutron stars start to break down and collapse in theory into a black hole. So they found one that had to be a neutron star because of the gravitational wave signal, but it was over the mass that is theoretically predicted. So
it was like 2.6 solar masses. And then
yeah.
the black hole was like 5. It was under like the small.
Yeah, so black holes they suspect that for a high mass star to smush down an object into a black hole, it had to be around 5 solar masses. So you might have read about the mass gap. That's
yeah, that's what it was on.
There's some cool ideas too. Some people hypothesize that there might be an intermediary stage between neutron stars and black holes called a quark star, where you smush the neutrons down to the next level of structure, and you basically just have a ball of quarks. But what's messed up about that is such an object would be so compact that it also would not allow light to escape in theory. So to the outside observer, it would be no different than a black hole. I don't know. The stuff's crazy, and it's certainly cool, all the new objects that we're finding with the gravitational wave detection. It's like a whole new way of looking at the universe. All right, so, you know, here I am riffing on black holes, but we got a job to do here. We have to learn about how to talk about the nighttime sky, and we actually have quite a bit of work to do today. So hang on to your hats. In our last lecture, we had an introductory bit on the motion of Earth. And I know I did some of it with you guys, but I could use a memory jog. I think we did the axis spin. I think we did 4 key points in Earth's orbit. Does this sound correct? Can anyone see that in their notebooks there? Andrew's saying yes. In that case, today we're going to start by looking at these things. We're going to need this eventually for our lab today. This is what your entire day is going to be consumed with, trying to understand how stars are pegged to this rotating sphere. Obviously, they're not actually pinned to it, but as far as you're concerned, if you're on a spinning Earth, the Greeks thought that the nighttime sky was a crystalline sphere with stars stuck to it. And while that's not the truth, it's actually more useful than the truth, because that's how you observe stars as they rotate over your head. And so this is a concept that actually is very useful to us. Hold on. I'm going to keep this handy because we'll probably need it at some point. But let's bust out an opening salvo here. Let's get a slide going. Let's start, I believe, with the celestial sphere. So here's a model of the celestial sphere. And we've oriented ourselves in space so that Earth's north pole is up. And we're imagining that all the stars are stuck to a single rotating sphere that goes around us, known as the celestial sphere. I also sometimes call it the global sky. You can see that there are 3 points of interest. Something called the north celestial pole, that's the projection of Earth's north pole. The projection of Earth's equator is the celestial equator, and this is the south celestial pole. Let's take that as notes, because I'm going to refer to these terms. Introducing the celestial sphere. The celestial sphere is a useful lie. It helps us keep our brains smart. I think I've chewed, this marker's almost chewed up, so I'm gonna give it a break. The celestial sphere is a sphere of infinite radius on which things like stars, suns, moons, and planets, hell, even galaxies if you want to go there, a sphere of infinite radius on which stars, sun, moon, and planets seem to rotate. Sometimes I draw a picture, but I kind of showed you one, so hopefully you've got the picture in your mind. Although you can feel free to draw one. The key points on the celestial sphere are the north celestial pole, which is the projection of the North Pole onto the sky, the celestial equator, and the south celestial pole. And I'm going to go out on a limb here. This might be true for me more than you, but the definitions of these things are pretty obvious. You just project the North Pole onto the sky. I'll give you one definition. So the North Celestial Pole is the projection of the North Pole onto the sky. And I could define the other points in exactly the same way. That word is sky, but it looks funny. All right, I'm now going to tell you something that is not obvious, something that should be explained to you because it kind of matters here. Make sure you guys got all that. I want to show you a picture, and I want you to think about this for a second. The note that we're about to take sounds like this. You can always see exactly 1/2 of the celestial sphere in your local sky. And I want to explain to you guys why this is not an obvious point, but I'm going to have to do so with a little marker here, okay? So imagine that you're standing where the arrow, the yellow arrow is pointing up. This is your dude. You're standing on Earth. You tend to imagine yourself as kind of like a little dude standing on a big Earth. And because you see yourself as small in comparison to the Earth, you might be tempted to think the sky over your head is a little dude sky that surrounds your little dude head. But I'm here to tell you that the sky over your head is actually a big dude sky. In fact, I've chosen my colors badly, but it's all of the green stuff that you see here. Let me clear that out. So everything that you see here in green is actually part of your local sky. And the reason why that's confusing or hard to understand is you tend to think that your feet, the horizon stretches out from your feet, which it technically does. But the Earth is so tiny in comparison to the celestial sphere, remember it's infinite radius, that there is effectively no difference between the line that goes through your feet and the line that goes through the center of Earth. Here, it looks like there's a difference because this picture is lying to you. It's making the Earth seem big in comparison to the celestial sphere. Perhaps a better rendition of this, I don't use this too often, the whiteboard, but I'm going to try to do it. A better rendition of this would be to imagine the Earth as a very, very small circle, okay? There's the Earth. And then the celestial sphere, oh, let me see if, how do I center this thing? Ooh, oh wow, I didn't realize I could do that. Here's the celestial sphere in comparison. So if you're a little dude and the arrow of your head is pointing, I don't know, like in that direction, then your horizon line, the line that goes through your feet is basically, in terms of geometry, the same thing. It's the same thing as the line that goes through the center of Earth. So the part of the sky that you can see is all of this. So your local sky always encompasses a direct 1/2 cut of the celestial sphere. I think that's important because it tells you things like, it tells you when stars rise and set that you'll expect them to be up for about 12 out of the 24 hours of the day. Let's take that as a note. oops, geez, I'm busting up the joint here. You always see exactly 1/2 of the celestial sphere in your, here comes a buzzword, local sky. The local sky is a concept in astronomy, and it's the next one that we're going to deal with. All right. Vanek, let me know when you're done with the notes. I just want to hear that I'm ready to erase, you know. You good? Okay. How about the rest of y'all? Sometimes when your heads are down, I can't tell if you're still writing or not. Okay. All right. Looks like everyone's good. I'm erasing. We're going to do a little Bob Ross time together here. Let me show you the picture that we're going to attempt to draw. Now, of course, I've provided you this picture both in lecture notes and in the PowerPoint slide, but man, it's really useful. It's really useful for us to recreate this, because by drawing it out, your brain will interpret it. So, oops. This is a diagram of the local sky. I'm going to teach you guys how to draw this. It can be a powerful problem-solving tool for your exam. So leave yourself quite a bit of headroom. By the way, can I make a recommendation to the class? For some of these drawings, and for many of our labs and lectures, getting yourself a 50-cent plastic ruler at the drugstore, at CVS or something, this will prove invaluable in our class. And if you really want to go above and beyond, for some sessions, since astronomy is so intimately connected to geometry, if you even go and just splurge maybe $2-3, buy yourself a crappy little compass and a protractor, when you make nice and neat diagrams, the thoughts in your brain are nice and neat. So there's really something to making a nice diagram. I'm going to teach you all how to do it. If you have a little plastic ruler, you can follow along with me. So let's make a 3-dimensional view of the local sky. Leave yourself a bit of headroom and make a line on your papers that's, I don't know, maybe 8 centimeters long or so. Mine's got to be a little bigger, so I'm going to make mine 60 centimeters. And, you know, use the edge of your calculator if you don't have a straight edge. And use your eyeball to kind of estimate where the center of the line is, okay? Now, we're going to try to draw a dome. My line was 60 centimeters, so I'll make it 30 centimeters tall. And I'm just kind of marking this dot as a reference point. And I'm going to kind of draw the best freehand dome that my money can buy. That's about as good as I can do free-handedly. I probably could have even done better than that. But there we go, something like that. Okay. Now what I want you to do is I want you to make a little dash above and below the central dot. This is going to help us make a sort of 3-dimensional ground here. So we can draw an oval in that connects these dashes. And this oval is basically the ground. Not too shabby. All right. I'll put a dude, an observer dude, in the center of the field here, okay? I'll even kind of shade in some grass or whatever, some sand if you're a desert dweller, or it could be some ocean if you're on the sea. It's very important when you draw a picture of your local sky that you choose and decide where the north, south, east, and west are going to be. This is a key point that you wouldn't think about. I'm a right-handed person, so by nature, I always choose north to be my right side, okay? So I'm north-oriented. And then I put south on the left. And then I put east here, and I put west over here. Now, this picture is going to be an important tool for us. I want to warn you, I don't know if any of you actually bought the book or are planning on it, but the book is very useful, but when the book does their diagrams, the book has a like a left-handed bias, probably because their drawings were done by some sinister left-handed artists who were responsible for drawing the pictures. And I think, depending on your handedness, you can be tempted to put north on the left-hand side. It doesn't really matter, except if you're new, if you're learning this stuff for the first time, then you're going to be wicked effing confused for most of this experience. So this would be an example of the book putting north in the North Celestial Pole on the left-hand side. So just watch out for that. If you're trying to follow some of the pictures in my slideshows, which I got from the book, they were done by sinister left-handed artists. We don't want to get confused by them, all right? So north is going to be on our right-hand side, and we're going to draw what are called the fundamental positions of your local sky. So these are the fundamental positions. These are vocabulary terms that I want to use with you. So let's start by drawing a line that goes right through your observer's head, right up to the top of the sky, and label that with a small z. This is your zenith. The zenith is the point overhead. Some simple definitions we'll do here, all right? Next, we'll talk about your horizon. Your horizon is the ring around the rosy that we made there, okay? It's a 360-degree ring. Wow, handwriting. A 360-degree ring at the base of the local sky. Actually, I'm going to say your local sky because the horizon is observer dependent. The horizon depends upon where you are on Earth. The horizon is not just a, you should not think of the horizon as a point on the ground anymore. You should think of the horizon as a point on the sky because stars can rise and set on your horizon. There's a name for the arc that runs north to south and cuts the sky in half. And that thing is called the meridian. The meridian is an arc that rises due north, reaches the zenith, and sets due south. I want to pause here and talk to you about the meridian. Let me give you a little sneak peek of where you're headed with this. I'm going to show you a picture, this picture, okay? It's a little much, but so is astronomy. The sky from now on is kind of like a giant rotating clock. Clocks were even based off of the sky. The sky was the original clock. And when stars rise in the east and set in the west, they follow these tracks. We'll later call them declination tracks, but they're these star tracks, and they're kind of fixed in your sky, but they're tilted at an angle towards the south. Now, this picture is very similar to the way that skies rotate through your local sky as a Rhode Islander. But if you travel north or south on Earth, these tracks will tilt in their angle. The important part right now is if you follow one of your stars, say a star in the red ring, which is your celestial equator, that star will rise in the east, and as it comes up into your sky, it'll make its halfway journey when it reaches the meridian. So the meridian, which cuts north to south through your sky, it's the highest point a star will reach on its journey through the sky. If you want to think about it in a clock sense, it's kind of like the equivalent of a 12 o'clock hand, right? Then the star will sink back down and set in the west. So the meridian is really important because once you know where north and south are and you have your meridian, you can look south and you can see this is the best time to observe stars, is when they're up there highest in the sky. Now, if we're in Rhode Island, we are in the northern hemisphere. And based on what I told you a few moments ago, that we can always see one half of the celestial sphere, we should be able to see the north celestial pole in our sky, and we should be able to see the celestial equator in our sky. Of course, there's almost nothing there, but we'll talk about that. So let's include these in our drawing. Let's also include these in our fundamental positions. I'm going to grab a blue marker. I'm going to make a line that goes from the foot of my observer, and I'll make it about halfway up the sky. Okay. I'm going to label it NCP for the North Celestial Pole. Class, there's a famous object which resides at the North Celestial Pole. Do you know what that object is?
Is it the North Star?
Indeed it is. Do you know the name of the North Star? Anyone out there? Adrian.
It's Polaris.
Yeah. Let me show you a little funsy picture here. We'll pretend for just a second like that this is the astronomy class that you thought it was going to be. We'll show you some constellations and stuff, okay? So let's have some fun for a second. Here's the deal with Polaris. Polaris, the North Star, is located very, very close to the North Celestial Pole. And it's actually the tail of the Little Dipper. The actual name of the constellation that encases the Little Dipper is called Ursa Minor, the Little Bear. But y'all, unless you've spent time in a very dark sky, you've probably not noticed this constellation before. From Providence, from Warwick, from Cranston, I can see Polaris, but it's not overly bright. And I can see this star, which is called Kochab, and I forget the name of this star, but I can see those three stars. These guys are totally washed out in our light-polluted sky. However, if you were to go to a very dark sky, like Block Island or somewhere out in the desert, this thing would probably pop right out at you. Most people are familiar with Ursa Major, or the Big Dipper. The Big Dipper has very bright stars that can be clearly seen from your backyard. Go and look for it tonight. And if you want to find Polaris, use the so-called pointer stars. So you make a line right through the front stars of the Big Dipper, and they almost point towards Polaris. You'll be able to find them in the sky. So make that a fun little observation project for yourself tonight, just so you can orient yourself in the nighttime sky. When you're out there, if you're just sitting on your deck, you know, having a beer at night or something, look up at the sky and see if you can find Polaris. That's a cool thing to do. If you take a camera and you put it on a tripod and you take a long exposure photograph, over the course of the night, this is what you're going to see stars doing. You're actually going to see stars rotating around the sky as Earth spins, and they'll be kind of circling around Polaris. Notice that Polaris itself is not quite at the North Celestial Pole. For all intents and purposes, we're going to just pretend like Polaris is the North Celestial Pole. In reality, it's off by about 1/2 degree. It's off by a moon diameter, but forget about that. You're not ready for that yet. Just pretend it's right there. Notice also that some stars are so close to Polaris in the sky that these stars never set below your horizon. And there's a name for these stars. They're called circumpolar stars. They will appear in your lab and in your homework this week. So I'm going to try to make a note about that. Just throw them in while I can. let's draw in a circumpolar star there. And I'll probably forget to define this later, so circumpolar stars never rise or set, okay? The last thing I'm going to try to draw in is the celestial equator. This is the hardest thing to, oh, by the way, can we put that down here in our fundamental positions? The north celestial pole. I also want to include in my fundamental positions, oh, the celestial equator. I'm going to do that in red. But before we do that, guys, let's put Polaris on our sky. I'll put a star right here. I'll label that star Polaris. That's because y'all are just learning. Now I'm going to try to draw in the celestial equator. I need to make a horseshoe or an arc that stays 90 degrees with respect to this line. I find this to be very difficult because I'm not endowed with that many artistic skills, at least not in the drawing sense. So that's my midway point, and I'm going to try to make a line that goes east to west. Let's see how it goes. Well, it's not great. That's about the best that I can do free-handed. And that's your celestial equator. And this is what your local sky looks like. This is how we orient ourselves in the local sky. We need ways to talk about the motions of stars, and we're going to use the horizon as one basis for that. Taken together, zenith, horizon, meridian, north celestial pole, celestial equator, those are the 5 fundamental positions of your local sky. And these are some vocabulary terms that I'm going to want to use on you guys, so get ready for that. For the rest of our day, we're going to spend our time trying to build up a system of coordinates to learn about how our stars rotate through the sky. I don't know if that's going to be fun, probably not, but it does help you if you actually ever become an amateur enthusiast and you want to get your own telescope. You'll find that this will be not only important if you want to look through a telescope, but also it's the fucking sky. You're going to be living with this for the rest of your life unless you become a ground dweller. So you might as well know what the hell's going on up there. You might as well know how to orient yourself and just have a basic familiarity with it because it's nature and nature's cool. So maybe that can be your pep talk to motivate you for this next section. We're going to do some coordinates, okay? We're going to talk about where we are on Earth because that will depend on what you're going to see in the sky, or rather vice versa. What you see in the sky depends upon where you are on Earth. Also, we're going to talk about 2 different ways to describe the motions of stars through our sky. So let's try to do that. Is everyone okay if I erase all my hard work here? All right. Speak now or forever hold your peace.
Was that last line in red? Right under.
Like celestial equator. If I write really low, my hand is in the way of the milk crates. It's kind of hard to do. So that's celestial equator.
Okay, thank you.
Mm-hmm. All right, so here I go. All right, let me give you a little top-down structure because this is going to take a little bit to get through. We are going to study 3 coordinate systems in this class. We are going to talk about geographical coordinates. That helps you figure out where you are on Earth. Then we're going to have 2 sets of coordinates for the sky. The first will be called the horizon system. That describes stars in the local sky. And then what the big buildup, which we're going to use in our labs today, this is all heading towards the equatorial system. This is a complete set of coordinates for the global sky. Honestly, these two things you may have heard of before, but probably are fuzzy about the definitions. This, unless you're an astro buff, this will be new to you, okay? So that's just, you know, a little, I don't want you to lose, this is going to take a while, so I want you to kind of understand where we're going with all this. So geographical coordinates first. Hold on, let me just give everyone a second here. Olivia, you still writing? Oh, by the way, before I forget to mention this, Olivia and Vinac, both, you had stuff today. You couldn't make the office hour session, right?
Yes, yeah.
But I have been recording this. So I think you guys already know the drill, but just to make sure we're explicit, after I upload the recording, you guys will go back and do the homework by following along with the recording, right?
Yep. Yeah.
You cool with that, Vinac?
Yeah.
Oh, actually, I was on it, but I'm not sure why you didn't see me being on it. I did the homework with you guys. I was listening.
Oh my gosh.
Was watching the whole video.
Oh,
but
were you, you know, I hide non-video participants. Did you not have your video shared?
Yeah, because I couldn't share my video.
That's okay.
But I said I was going to be on.
So the only, I just want you guys to know, so I can focus on the people I can see. I hide non-video. Like there's 3 people trolling in the background. I can't remember who the hell they are. Oh, Ernest, Nick, and Janabelle. So I hide non-video participants so I can focus on the people I can see. And that's one of the benefits of, I mean, there's no reason you have to do it, but it actually helps the class and it helps me. Shoot, how do I hide the people now? I just fudge. Okay. Video settings, hide, video, non-video. All right. So that's why I didn't notice you were there, Vinac.
Okay. So I just have to send it in, but I'm still having trouble like getting it in the JPEG because it comes up like as a file attachment.
What kind of file?
I mean, I took a screenshot of it with my phone and then send it to my email.
Okay. Are you using an iPhone?
Yep.
Okay. So I need you to go to your camera settings. Can you do that for me? Go to settings and scroll down till you see camera. Right?
Yep. Camera.
All right. Do you have a tab there that says formats?
Yep.
So go into that, and what's it set to?
Because I set it to most compatible when we last did it.
Oh, hold on. Hold that up closer. So it's on most compatible. Hold on. Let me. You keep that right there. Don't you move. All right. Most compatible. Okay. When you go to your camera, now go to your camera real quick.
Yep.
And I can tell you what might be going on. Show me your camera for a second. Do you see that there's a button usually up at the top that's HDR or something?
No, let's see.
It's hard to see. There should be a button for high dynamic range. You want to turn that thing right off. You just want the stupidest, smallest, simplest picture. The problem is your phones are too good now. The pictures they take are these crazy high dynamic range ones, and they're huge files. And Blackboard was, of course, designed by frumpy middle school teachers who couldn't imagine a file size needing to be bigger than 2 megabytes. So they're like, oh, that'll be fine, 2 megabytes. That was great in 1972, all right, but it's not good anymore, guys. Increase your fucking, I'm talking to you, Blackboard, if you ever watch my videos, whoever you are, increase your stupid file sizes and get with 2020, okay? So anyways, I've got this. So we got to figure out how to take a smaller picture with your bazooka phone, okay? Do you see the high dynamic range button, Vinac?
This is what is showing up.
Yeah. All right. So it's hard to see. One of them damn buttons. Oh man, I don't even see. I'm rocking the iPhone 5, so I'm like, I'm kind of becoming one of these out of date people. So
I mean, we don't have to do it now. It's
we'll figure it out.
I can do it after. Yeah.
But this is relevant not just to you, Vinac, but other people are having these issues, which is why I think it's worth talking about in the group here. But why don't we just save it? Here's what we'll do. Trial and error. At the end of our lab today, we'll all submit it like we did last time, and we'll see who's good and who's not good, okay?
Okay.
All right. Maybe you know what you could do? You could trick it into taking a lower res picture. I think the front camera is a crappier camera. So you could like do it like you were taking a selfie, but then selfie the picture. That might be a way to trick it into taking a lower resolution photo. I didn't think about that till today. All right, guys, let's get into the equatorial system, okay? That determines where you are on Earth. Let me go to my view here. And our geographical coordinates include two angles. There is latitude and there is longitude, okay? And I'm going to define these for you real quick. Latitude is your degrees north or south of the equator. So where's my damned Earth here? Remember the mnemonic device. Latitude is like a ladder. They're horizontal lines, but they measure north or south. So if you get up here on my globe, you can see a constant line of latitude there. I'm guessing that's probably around 23.5 degrees north. That's probably the Tropic of Cancer. Should label it somewhere. Oh, no, sorry. That's 15 degrees north. This is the 15-degree parallel, as they say. They call them parallels because they're parallel to each other. Longitude is going to slice the Earth like tangerine slices, just like this is a slice of longitude right here, this ring, okay? And the thing about longitude is, unlike latitude, which has a natural starting point at the equator, there's no good tangerine slice of longitude to start on. You've got to kind of arbitrarily pick a place on Earth to start measuring longitude at. And a bunch of people got together, a bunch of astronomy-minded people, and they decided that the so-called prime meridian, the 0th line of longitude, was going to pass right through the front door of the Royal Greenwich Observatory. Where are we here? I got a sweet little slide of that. So Greenwich, England is just outside of London. You can think of London and Greenwich as being the same. This is a picture of the Royal Greenwich Observatory. And if you go and visit the Royal Greenwich Observatory, oops, that is not what I meant to do. I was trying to be on my slideshow there. The so-called prime meridian is a line of longitude that passes right through the front door of the Royal Greenwich Observatory. And you can go visit the Greenwich Observatory, and if you do so, you can stand here at this line, and you can take a selfie, all right? And that's cool because then you have 1 foot in the Western Hemisphere and 1 foot in the Eastern Hemisphere. It's like a thing that people do. And as a matter of fact, one of my former students visited Greenwich, and they brought me my very own Prime Meridian pencil from the gift shop. This is now a treasured item on my cart, and I will not let you borrow my Prime Meridian pencil. This one's for me, okay? But feel free to send me a gift from the Prime Meridian gift shop if you ever end up there. Longitude is defined as degrees measured east or west of the prime meridian, all right? As an example, it might be nice to know the latitude and longitude of your own fair city. Providence, Rhode Island is at a latitude of 42 degrees north, and it's at a longitude of 71 degrees west. As a matter of fact, your iPhones, where is my iPhone? Hold on. Your iPhones are actually sophisticated GPS devices that should be able to tell you your latitude and longitude to a pretty high degree of precision. Let me see if I can remember where to go. It's been a while since I did this, but I think if you go to your location services, does anyone remember how to do this? I'm about to run out of battery time here. Somewhere in your location services, it will actually tell you where you are. Damn it. I actually think this is worthwhile doing because this is a teachable moment here. Let me just type into Google, find latitude and longitude on the iPhone. I know some of you don't, oh, we can open Google Maps. Oh, I want to see where the GPS coordinates are. 3 ways to find GPS coordinates on the iPhone is, all right, so they're telling us to do maps. Oh, the Compass app. Cool. Let's try, do you guys know where your Compass app is? This could be useful if you're ever lost in the woods or something. I tucked mine away somewhere. Here we go. This is my Compass app. You guys will see we got some GPS coordinates right there. Do you guys have this in your phone? I've got 41 degrees. Oh, what are these things again here? 49, whatchamacalls it? And 24 what? What do these little things say?
Arc minutes and arc seconds.
Yeah, looks like they're using those things. They took my astronomy course, I guess. So they know about that stuff. 71 degrees. By the way, it's kind of cool because we're all in physical different locations. We should be at least arc seconds and sometimes even arc minutes off from each other. So who's got their phone out right now? Megan, do you have yours? Or Janabel, can you read me your complete latitude and longitude so I can compare it to mine? Wait, actually, first I should ask you, what city are you in? You're muted. I can't hear you. Wait, Janabel, you're muted.
Sorry, I'm in Providence, but sometimes in different GPSs, I'm like in that one street between Providence and Cranston.
Okay, so you're a little bit away from me. Is anyone down in South County, or is anyone down south? Further away from me and Janabel?
I'm up north in
Oh.
Mass.
You're in Mass? Okay, so what's yours say, Tim? Do you have yours out?
42 degrees and 9 arc minutes
Oh, wow.
latitude.
So yeah,
And
you're
then-
pretty far. You're pretty far. Well, you know, you're over a degree north of us. That's kind of cool. Oh, Nick's got 41. Okay, yeah, Nick. And what town are you in, Nick? I'm glad that Nick's participating here in the dark. 41, 51 arc minutes, and I've got 49 arc minutes. So Nick, you and I are 3 arc minutes off in North Providence. Okay, so cool. So you can see even just going a town north or a town south, we're changing by a few arc minutes all the way up to a degree once you get to Mass. Let's see you guys try it. How about the North Pole? So can someone who has bravery tell me the coordinates of the North Pole? Latitude and longitude. Who can do that? No one? Adrian, you want to give it a whack?
Is it 90 degrees north, 135 degrees west?
90 degrees north is correct. But that's not the longitude.
I would have assumed it was like.
Honestly, I kind of give you a tougher challenge than you might realize. Adrian. I want you to look at a picture with me. You see this? What's going on there? What's happening at the North Pole to our lines of longitude?
They're all going right there.
They're converging, right? This is weird. It means, technically speaking, that the longitude of the North Pole is undefined. It's probably the only place you can go and have an undefined longitude, that and the South Pole. In mathematics, we call these points degenerate. A degenerate point is one that is multi-valued. The reason why that's okay is because if you are at a latitude of 90 degrees north, that is a unique location on Earth which can have no ambiguity about it. So 90 degrees north is the North Pole, and there is nowhere else on Earth you could be. That is not true of most lines of latitude. You could be at a latitude of 30 degrees and be in South Carolina, or you could be in California or Colorado. So you could be at a whole bunch of different places, or actually I think Arizona is at 30 degrees north. So there's a bunch of different locations that'll pass through this, or that this line of latitude will pass through. But at 90 degrees north, you are at a unique place, the North Pole. The longitude is undefined. Fans of mathematics will discover that when you create coordinates on a curved surface, such as the Earth or some more abstract manifold, on a curved surface, a coordinate system will always have two degenerate points that are multi-valued. So this won't be the only time you see that. All right, let's erase this and let's move on to the horizon system. Any objections to my erasing? Now we want to talk about stuff that's on our sky. Introducing the horizon system. Your horizon system is your sort of default looking up at your sky coordinate system. You use it in the local sky when you're standing at a telescope with your friend. It uses two angles. The angles are altitude and azimuth. The altitude is defined as the degrees above the horizon. Actually, if we want to be uber technical, degrees above the nearest horizon. Because the horizon's a ring. You have to decide what point along the ring you start. The azimuth is defined as your degrees along the horizon measured clockwise from north. Just take us, actually, let me get some water while you guys write that down, and then we're going to test out our ability to understand this. Let me get a slide up. Keep that there, stare at it for a second. Actually, I'm going to give you guys a question to ponder, okay? This star in black, when I come back, I want someone to give me a reasonable guess as to its altitude and its azimuth. But I'm fearfully thirsty, so give me a second here. You have to get your own water. Okay, guys. If you understand this stuff, which you may not, we're trying to understand it. Someone brave enough to try to just throw a number out there, what they think the altitude or the azimuth of this star could be? The altitude should be easier.
45 degrees.
Yeah. I mean, let's see. Up here would be 90. Down here would be 0. We're kind of looking in a three-dimensional perspective, so it's hard to gauge exactly what that angle is. So 45 degrees is actually totally reasonable. Very, very reasonable. What about the azimuth? To do azimuth, this is the nearest point on the horizon, but we have to start north, and we have to swing all the way around until we get to there. How many degrees do you think that is? Maybe this would help if why don't we define the degrees north, east, south, and west first on the screen here. So azimuth is kind of like direction. So what would the azimuth of due north be? This is supposed to be in softball, guys. An easy one.
0.
Yeah. How about east? Someone besides Tim, so I know that I'm talking to at least more than one person here. The azimuth of east, can you do it? Oh, hell no. Hell no. Look, here's your local sky. There's north. That's 0 degrees. How many degrees is it to east? Megan, I volunteer you to answer this question. You've been volunteered.
Okay, can I guess 80?
Hold on. Do you know your circle? What's a 90-degree angle? Oh, fuck.
What?
90 degrees, right? I tried to ask you how many degrees are in a right angle, and I asked you how many degrees are in a 90-degree angle. So I screwed up. I told you the answer.
90 degrees.
Yeah, there you go. Look, perpendicular lines. When two lines meet and make a capital T, that's 90 degrees, okay? So, all right, so Megan, what would due south be?
180.
Yep. How about west?
360.
No. 360 is all the way around.
My bad.
West is 180 plus 90.
270.
270. Considering that due west is 270, could you give me a reasonable guess as to the azimuth of this star, considering that if this is north, then that's south, and this is kind of a three-dimensional thing here. So that's east and west. What would you say that the azimuth of that star is? No?
Would it be over 270?
Yeah, so pick a number that's greater than 270 and less than 360, but a little closer to 270.
310.
Fine, I like it, 310. That's a reasonable guess as to the azimuth of that star. We need to do this. We need to practice using the horizon system in order to learn the horizon system. I've got an idea of how we might be able to do that. Let's play a little game together. I'm going to teach you guys how to draw a two-dimensional view of your local sky. It's going to be helpful. So I'm going to erase. Let's give this a shot. Actually, first of all, no. Let's do the picture first, okay? So let's make a 2D view of the Rhode Island local sky. Sorry, Tim, but we're biased towards Rhode Island. You mass holes don't get a say here, right?
Rhode Island's whack.
Yeah, it's true about this whack, but whack is cool sometimes. All right, anyways, let's start by drawing our line. Okay, let's make it 60 centimeters. All right. I'm gonna do the same thing I did before. I'm gonna do the dome. The only difference between this diagram and the one we made before is I'm not gonna really bother with the three-dimensional part. I'm just gonna kind of draw the dome here. Well, could be better, could be worse. Let's put an observer at the center of the field. North will be on the right, south will be on the left. I'm actually going to go ahead and I'm going to draw my observer's zenith right in there. All right. So there's your zenith. I'll just shade in the ground here to remind myself this is down. Making a diagram like this can be very helpful, especially during an exam when you have to answer tricksy questions. Now, you guys know that the North Celestial Pole will be somewhere, Polaris will be up in your northern sky. So, I don't know, halfway up, let's draw in our North Celestial Pole. Okay, let's put Polaris on the sky. The sky is the dome there, so here's Polaris. I can't draw in all of the celestial equator because the celestial equator is a decidedly east to west affair. What I can do is draw the angle that the celestial equator makes with my meridian. This, of course, don't forget, is called your meridian. And I know that the celestial equator has to be perpendicular to the equator because, duh. How many degrees is that again, Megan? From here up to here?
90.
Yeah, okay, good. So those two things are perpendicular to each other. So I'm gonna make a dashed line for the celestial equator. Let's see if I can do this. Okay. CE. This is a nice two-dimensional view of your local sky. I'm going to go ahead and I'm going to label some angles here. Now, let me get crazy on you for a second. I'm going to use the first 4 letters of the Greek alphabet. This is a time-honored tradition. The Greeks loved geometry. And today in mathematics, when we represent angles, we often do it with Greek letters. It tells the reader this is an angle, not a distance. So this is alpha, beta, gamma, and delta. These are the first 4 letters of the Greek alphabet. Alpha, beta, gamma, delta. See if you can reproduce those. Now, Tim had to learn this in his 1020 class because both of my courses have to learn about stellar coordinates. And that gives Tim a slight edge on you guys. So we'll keep him as a reserve chess piece if we get really confused. Tim, you're the backup. The rest of you guys are kind of new to this, so you need to go through the ropes here. One of these angles, I call this the alpha, beta, gamma, delta game. One of these angles is a direct representation of your latitude on Earth. Can you guys guess which of these letters, alpha, beta, gamma, delta, refers to your latitude? Based on the definition of latitude, Adrian, maybe we could get you to read the definition of latitude once more for us.
Degrees north or south of the equator.
Okay, you want to take a guess?
Alpha.
Not alpha.
Delta?
Not delta.
North.
You might as well keep guessing. You got 2. Oh, I'm sorry, Janabel, did you say something?
It goes from north to south, so north first. No.
Maybe this would help. Imagine that you put the Earth below you. That's a ball. It's not going to work. Let me try a disc here, okay? Imagine simultaneously trying to think about the curvature of Earth. You don't think about it, but latitude, longitude, they're angles. They're not distances, they're angles. It's a geometry thing. Hold on. Here's the north-south line. Same orientation. The equator is perpendicular to that. Ah, fudge. Right? And you are a dude or dudette who is standing here, right? Adrian, how did you define the latitude again?
Degrees north or south of the equator.
So this dude's latitude is that angle there, right? So Adrian, you want to refine your guess? Or anyone? Adrian, I thought since we were picking on you earlier, we could just keep picking on you.
I'm not sure for this one, I'm sorry.
Okay, all right, that's fair.
Data?
Who said that? Who are you? Wait, who said that? I couldn't see all your, oh, Megan, yes. Megan, you are correct, beta. Look, Megan can see that the equator should point up towards the celestial equator, right? And Megan can also see that the feet should point towards the head, towards your zenith. So if the latitude is the degrees of your feet sort of north of the equator, then that angle is the same as, it's basically, this is your zenith and that's the celestial equator. So let's label that. That's your latitude. Good job, Megan. All right, Megan, since you're so good, since we're going to keep talking to you, what if I asked you another tricksy question? One of these angles, alpha, beta, gamma, delta, is a direct representation of the altitude of Polaris. Which angle would represent the altitude of Polaris? And while you're thinking, maybe Adrian could read us the definition of altitude again, just to remind the class.
Altitude?
Yeah.
Degrees above the nearest horizon.
Okay. So Megan, do you have any deep thoughts about which letter could represent the altitude of Polaris?
Sure, I'm going to guess gamma
Not gamma.
and delta.
It's got to be, it had to be one of those two because those are the angles that touch Polaris, right? But remember, it was not defined as how many degrees off of the zenith. It's defined as degrees up from the horizon, right? So this is the altitude of Polaris. It's the degrees the star is above the nearest horizon, okay? The nearest horizon in this case being north. This, by the way, let's label this. This point is your northern horizon. This point down here is your southern horizon. I would like to point out to the class that this line is not your horizon. This is the ground. The horizon is a three-dimensional ring going in and out of the board, okay? It only intersects this diagram in two places. Now, what did we say our latitude was here in Rhode Island? Megan? I'm just gonna keep calling on the same people for fun.
I'm not in Rhode Island, so I can't recall.
You disagree. You're not in Rhode Island, so you object. Are you in Massachusetts or Connecticut?
No.
Oh.
Yeah.
You're in some exotic locality?
Yeah, I'm in California right now.
Wait, right now you're in California? Holy shit. That's amazing. Okay, I forget, I'm so used to you guys having to be here, wherever here is. You are in California. Wow, so oh, you have to get up 7 a.m. for this class, huh? Sucks to be you. All right. Anyone remember the latitude of Rhode Island?
41.
42 degrees. I think it was 41 on my phone, but we're going to go with 42. The official latitude for this class will be 42 just because it's easy, okay? We have to pick one number. Let's stick with that. So we'll label this as 42 degrees. By the way, Megan, just because you're not in Rhode Island does not mean you're not obligated to memorize our latitude and longitude, for the record, okay? All right, so now I don't know about you guys, but I spy with my little eye a right angle. It's a 90-degree angle between the equator and the North Pole. So what would that make gamma, friends? If this is 42, what should that angle be? How many degrees, Megan?
90, so it would be 48.
Yeah. 90 minus 42 gives us 48 degrees. And yet, I spy with my little eye another 90-degree angle. This one between the zenith and the horizon. So what does that make delta? Anyone at all? Bye.
42 degrees.
Yes. Now, for complete purposes, let's also label alpha. What should we label it?
48 degrees.
Yeah. Now, the angles 42 and 48 are specific to Rhode Island. Sorry, Megan and Tim. However, the principle that we just discovered is the same anywhere you go on Earth, because there'll always be a 90-degree angle between the equator and the North Pole, and there'll always be a 90-degree angle between the zenith and the North Pole. We have therefore proved a very useful result in astronomy and in life in general, and it goes like this. The altitude of Polaris is equal to your latitude. And because this is a fundamental result, we should box it and we should star it, because this can help you solve tricky problems, right? So when the CIA comes to your house and puts the hood over your head and you get extraordinary rendition and you wake up in the forests of Germany after getting cold cocked, you're going to feel confused. And if you can find Polaris, you'll know what your latitude is. You'll be able to orient yourself on Earth so that you can run for help, okay? There's a reason we're putting a star around this. We're going to use this to solve some of our homework problems next Monday, all right? And I want you guys to be able to whip one of these out in a jiffy. You can scratch this onto the back page of your test, and it can help you solve some problems when they come up. I'll give you some examples. Actually, let's do a couple of sample problems that are actually from your homework. We'll kind of prime the pump, and we'll see how you guys deal with it. This will also give you a sense of how I could deploy this against you in an exam, so you kind of know what to expect. I'm going to erase all this. Is that cool? Anyone still note taking there? Okay. I got some thumbs up from everyone. All right, I'm going to erase this. So let's imagine that this was a typical question that I would ask you. It's one of your homework questions, and it would go like this. Describe the location of Polaris in the Rhode Island local sky. Now, I want to see how much hand-holding you guys need here. Does anyone know what the answer is, or how to, does anyone know how to answer this, like what I'm looking for here? Here's a hint. I want you to use the horizon system. Janabelle, what do you think?
We're gonna do, so the horizon system is a local sky.
Right, so walk me through this. If I want to use the horizon system, what are the two angles we need?
South, north.
This is why I taught it to you. What are the two angles in the horizon system, Janabelle?
North and south.
No. Look in your notes there. Do you have notes from a few pages back or a page back? Look under horizon system. What do you see are the two angles? The two coordinates.
360 degrees.
Show me your notebook. I just want to, you know, sometimes I'll walk around and I'll just look at people's notebook. Hold on. Put it right up to the damn screen here.
This is one page.
Okay. Oh, no, it's past, oh yeah, past that. Next page. Oh, yeah. Oh, wait, up top. Yeah.
My handwriting is really bad.
Yeah, it's right up top. The two angles.
Altitude degrees above the nearest horizon.
No, I don't need the definitions, just the names of the angles. Does anyone understand what I'm asking? Because it may be that we're not translating to each other here. I'm looking for the names of two angles that are used as coordinates in the horizon system.
Altitude and azimuth.
Altitude and azimuth. So that's what I was looking for, Janabelle. Do you understand now?
Yes, okay.
Okay. This is part of the reason we do this is so that you guys learn how to talk to me and learn what I'm asking, okay? So in other words, Janabelle, let's keep hammering on you for a second. I want to describe Polaris, and I need an altitude and I need an azimuth from you. Can you give me either of those based on the thing that you just learned and put a box around? What would the altitude of Polaris be in the Rhode Island local sky?
The latitude.
Which is what? I want a number. I want a hard number.
I'm not sure what the numbers will be, but I know what the definition will be.
Well, the reason why you would know the numbers, Janabelle, is because we wrote them down right on the alpha, beta, gamma, delta game, right? I wrote them down for you.
Oh, okay, so it's the same. We're going to base it off this, what we just did?
Yeah, because that's for the Rhode Island local sky.
Okay. All right, so the altitude degrees above the horizon is going to be 42 degrees.
Good. What about the azimuth?
And the azimuth is going to be...
Here we're going to need to remember the definition of azimuth if you're going to do this.
Okay. 48 degrees?
No. Let's find the definition of azimuth and let's regurgitate it.
Degrees along the horizon clockwise from north.
Clockwise from north. So
Okay.
this is going to be kind of a funny question, but what direction is the North Star?
To the right?
No, because if you turn around, it's to the left. So that's not good enough. We can't do right and left anymore. We need to have concrete See, look, what we're trying to avoid, Janabelle, is, and if I say describe the location of Polaris, I don't want people saying, oh, it's just to the left of the tree, just past the little pine cone there. That's not going to do for proper communication. We need to have specific numbers. I now know that I have to look 42 degrees up, but I do not know in which direction I need to look. Azimuth tells you the direction. So what would the direction of the North Star be? Anyone? Does anyone understand what I'm saying?
Yep.
Okay, Tim does. But Tim, you can't talk here. You know what? No, Tim, we're calling in our reserve chess pieces. Tim, what direction is the North Star?
North.
Yeah. All right. And what is the azimuth of north?
Undefined.
No, 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 no. No, it's well defined.
Zero.
It's defined as degrees from, yes, degrees from north. So if you're north, you're 0 degrees. Azimuth is a direction. All right, that took a little bit of squeeze in there, guys. Hopefully we're gonna get better at this. You're definitely gonna wanna be there for office hours next time, because this is one of the easier questions, all right? Before we go to tea break, let's try one more. This one's gonna be more challenging. Question 2. Describe the path of the celestial equator in the Rhode Island local sky. Okay. Answer 2. I'm going to help you out here because this one's tricky your first time around. The first thing is you got to realize it's an arc or a semicircle. That looks like a single word. And an arc is not a point. It curves across the sky, and we're going to need 3 points to describe it. And my nicknames for these points are the rise, the reach, and the set. Unfortunately, each of these points will have its own altitude and azimuth because we're still using the horizon system. That's a total of 6 numbers to describe this path. My handwriting sucks, so all right, let's just go with this, okay? All right, let me walk you through what these points are. Let's do a share screen here, and let me show you the all-important slide of your local sky. So I don't know if you guys can see what I'm talking about here, but let's say this point here, that would be the rise, okay? Because stars usually rise in the east, right? Up here, that's the highest point of the celestial equator's journey. That is the reach. And down here, that point is the set point. Those are the 3 points I want to describe. Sorry. Matthew, you're up. Do you think you could explain to me the altitude and or azimuth of that point right there?
So the altitude would be 0.
Very good.
Degrees.
Because it's on the horizon. And how about your azimuth or direction?
90 degrees.
Or east, right.
East, yeah.
So we can actually say either one, 90 degrees or east. I'm going to put both versions on my board so that you guys can see that either one would be acceptable. Azimuth and direction are the same thing. In fact, the name of this, we call this due east. Okay, that was pretty good. Vinayak, do you want to give this a whack? What would the reach point be? So, Vinayak, you might want to use your alpha, beta, gamma, delta table there for help.
Mhm.
And I want the altitude, the number of degrees this is up, and I want the azimuth along the horizon. So according to that alpha, beta, gamma, delta game, what would this angle be here?
Um, 48.
Excellent. So that's your
Yeah.
altitude is 48 degrees. What about
Yeah.
the azimuth? That you're just going to have to remember how azimuth works, right?
Mm-hmm.
Look at my screen. So Vinayak, azimuth is starting north. You go along the horizon clockwise. How many degrees is that? For this point, let me explain what's going on here. To get the azimuth, you need to find the point which is closest to your point on the horizon. Since this point is closest to that point on the horizon, we have to measure how many degrees is that from north.
Would be 180.
Very good. Nice.
Because there's 290 degrees angle on both sides, right?
Right. South is 180 from north, exactly. And 180 degrees is the same thing as south. And Andrew, do you want to give us the set point?
I can try. I can try.
All right, my arrow is pointing to the set point. I want an altitude and I want an azimuth.
Would it be 42?
No. Also, I'm not sure which angle you were giving me there. Let's start with the altitude. The altitude is the degrees above the horizon. So how many degrees above the horizon would that point be?
I don't know.
Well, the horizon is the black ring, right?
Yeah.
And it's on the horizon.
So it'd be 0.
That's right. It's 0 degrees. What about the azimuth? The azimuth starts north and it goes around clockwise.
So would it be west?
West is the azimuth. What's the technical number, the number of degrees?
270.
Very good. Okay, so that wasn't so bad. You did that. So the set is 0 degrees, 270 degrees for west, which is the same as due west. All right. I think I've cooked your noodles a little bit here. We still have one more coordinate system to go, students, but I'd say y'all look like you're ready for a little tea break. Yeah? You want to take a little pause? Relax the mind? One thing I could mention is because at the end of our lecture, we're going to go into our lab today. Should we all try to print out today's lab manual is a little more intensive. It might be difficult to write this down. Get out of here. Oh boy, I need a tea break. Let's just quickly look at our lab for today, because during tea break might be a time you guys can print this out. You need the Celestial Spheres PDF. This might be a little irritating to have to redo. So if you can print that out, that'd be great. Does anyone not have a printer? Destiny. So Destiny, Oh, see, Destiny, you hid from me, and then I didn't torture you with my questions, but I'm going to come back to you, Destiny. Don't you worry. Destiny, let me give you a suggestion of what you might be able to do. First of all, I'm going to hit print. I might have this as a Word document. And Destiny, do you have Microsoft Word, or can you use it through the school or something?
Yeah, I do. I actually figured out a way to transfer it to a Word document, so it's all set.
Oh, you already did that? Does it look good? Here's what it looks like on mine. Does it look nice and neat like this?
Yeah.
Oh, so you're ahead of me. You were already doing this.
Yeah.
Okay, cool. That's great. Anyone else think they're going to have issues, or will the rest of you be able to print it or something? I just want to make sure no child left behind and all that, you know?
I don't have a printer either.
Andrew, so do you have Microsoft Word?
I might. I think the last time I tried to use it, it said I had to buy it.
Okay, in that case, because this issue happens, the school provides you with usage of Microsoft Word, but you have to go through their system. And I got to remember, do any of you use Microsoft Word through, first of all,
you can use Word on your Outlook email to have everything.
on the Outlook email, that's right. So thank you. So Andrew, if you go to your Outlook, your mail, do you see these little dots here?
I'm going to go to it right now.
If you click on these dots, you can click Word right there. And I'm going to share the file with you. I can do this. I can share.
Can you share it with me too?
Yeah, share file.
Yes, and with me, just in case. I haven't used my printer in a while, so just in case.
Yeah. This is one where you should be able to type it in, but hold on. How do I share? You know what? I'm going to put it into the chat box. Let's try that. I've done that before. In the chat box, I'm going to select a file from my computer. I'm going to select stupid dummy. Stupid dummy. Okay. And here's my Celestial Spheres lab. Boom. Hey, network disconnect. What the shit? Did you guys can hear me, right? We're still talking. Why would it say network disconnect? All right, I'll have to try this yet another way. Let me try emailing the class. I should be able to attach it here. This is my least favorite method, but I'll just call it LAB2. And where's the bloody attachment thing here? Help me, guys. Help an old man use the internet. Oh, here we go. Attach a file. All right. All right. And then black terabyte, 1010 labs, and celestial spheres. Okay. You guys, yeah. You guys get that? I just sent it. So Andrew, did you figure out how to use Word from your computer with the 9 dots there? Talk to me.
Yeah.
All right, so you can.
Yeah, I want on the
So you click Word through there, and this means everyone will be able to use it in some capacity. You can type it up, or you can write it out, whatever your preference. In fact, most of you might want to just type this one up because it's pretty simple to do. All right. All right. So why don't we take a nice half-hour tea break? We'll come back at 12:10. I'm sorry. Wow. We'll come back at 2:10, and we'll resume our lecture. Does that sound like a plan? All right. I'll see you guys in a little bit. Do it. All right. Welcome back, everyone. In the second half of our course, we're going to do equatorial coordinates, which I was just talking with Tim about. But we're also going to learn some new stuff about sidereal time and the rotation of Earth. So in order to answer that question, Tim, I need to build up a few blocks for us to stand on. And let's just start off with a couple of fun tidbits that are not complicated, but you probably never thought about them. And the first will go like this. There is a conversion between angle and time in astronomy. And it's about the rotation of the sky. So here's planet Earth. And Earth is obviously spinning on its axis in 24 hours. And depending what your, oh my gosh, I took a little nap during tea break and it's left me disheveled here. Whatever latitude you're at, you're gonna rotate in a 360-degree circle, okay? Now, if you divide 360 by 24, something interesting happens. Why don't you guys try it? What do you get? Got a number for me?
15.
Exactly 15, and watch the units, 15 degrees per hour. Huh, isn't that interesting that it comes out to be a perfect number like that? You know, there's a reason for this. You can thank the Babylonians who invented the hour as a 15-degree wedge of the sky. Like the division of the sky up into these chunks was very intentional, and it was first done by the Babylonians, who I think invented the hour before Egyptians did. I gotta get this thing under control here. This means in astronomy, there's a kind of weird conversion factor that normally doesn't make sense anywhere except in astronomy. And it goes like this. 15 degrees is equal to 1 hour of sky rotation. The reason why that's important, several of your homework questions are going to depend upon this. And in particular, it allows for different ways of measuring the positions of stars in the sky. We could use angles, but we can also use time. We can use the natural rotation of the sky. This is something that's irritating to learn, but it's very useful when you're actually at a telescope. Now that's one of my tidbits points that I had to build up with you. I'm going to erase this. Shout at me if you don't like that. The other is to discuss something called the spring equinox. When I introduced the spring equinox, I introduced it as a point in Earth's orbit, where if this is the sun and Earth's orbit is a circle, the spring equinox was that day when the axis tilt of Earth makes a 90-degree angle with respect to the sun. In other words, on the day of the spring equinox, the Earth looks like this. If you guys are the sun, if my camera is the sun, this would be the spring equinox when the equator is pointed towards you, the viewer, and the sunlight falls equally on northern and southern hemispheres, and the celestial equator points towards the sun. But the spring equinox is actually many different concepts all at once. So the spring equinox is 4 things at once. And this can be hellishly confusing for new students. The first is it's a point in Earth's orbit. Because each point in orbit is pegged to a day, it's also a day of the year. And the day is usually somewhere around March 21st, although it could vary from the 20th to the 23rd, depending on which cycle of a leap year you're in. Here's a fun one. If we take an Earth-based reference point, the spring equinox is also a point on the sky. Sorry, that looks weird. That looks like a foreign language. And this is this is a little confusing, so I might need the help of a diagram here. Let me show you this thing. Here you can see the celestial sphere, but there's a couple of things going on. First of all, it's an Earth-based reference frame, but look what they've gone and done. They've gone, done, and did it, and they tilted the orientation of Earth by 23.5 degrees, so that instead of the celestial equator being horizontal, Now the ecliptic is horizontal. Aw, dang, I'm using my $10 vocab words on you now. And that's when people get lost. Can someone out there remind me what the definition of the ecliptic is in this context? This is definition number 2 of the ecliptic. I don't want to be confusing you all with my fancy words, and I'm worried I'm doing just that. What is the meaning of the ecliptic?
The path of the sun through the celestial sphere.
Yeah. So this is the path that the sun takes against the background stars. This is where the zodiac constellations are, right? You'll notice that the spring equinox can be thought of as the point where the celestial equator intersects the ecliptic. And that actually jives with the other picture that we had, because if you guys in the camera view are the sun, when the celestial equator points directly towards the camera, you guys are the ecliptic, and that's when the two kind of intersect each other. But what that means, guys, is the spring equinox, if it's a point on the celestial sphere, well, doggone it, that point is going to rise and set every day along with the other constellations. All right, shucks, that's not what I wanted to do. That's not what I wanted to do. That's not what I wanted to do. Hold on, I'm confused here. Fuck, get out of my way. Okay. Here. The spring equinox, I have a sensitive mouse here. Okay. The spring equinox shown here is the point where the ecliptic and the celestial equator meet. But here we go. Look, this point, somewhere below the foot of Pisces, what is Pisces, a fish? Somewhere below the gills of Pisces, the spring equinox is a point on your sky. And that means it rises in the east and sets in the west every day, just like any old star in your sky. But you've never noticed it before because usually there's nothing there. Most of the time, it's just an empty spot on the sky. Except for once a year, a special star will appear for one day only at the spring equinox. Do you know what star I'm talking about? One day a year, a special star will appear at the spring equinox, just once a year. Tim, do you know what I'm talking about? No?
No.
Special star? Anyone out there want to guess what that star is? Olivia, you got thoughts?
Sorry, is it the one that's circled? I just had to step away for a second.
Oh, okay, sorry. Yeah, it's the spring equinox is a point on the sky. And I'm trying to tell you that it's an empty point. And I wanted to say something like there's nothing there ever. And then I realized, oh wait, one day a year a star appears there. And I just wanted to know if you guys could guess what that star was.
Oh, okay. No, I don't think I'm familiar with it. Yeah, pass.
Matthew? You're the next box down. That's what I'm calling on you.
I'm going to take a wild guess and see the sun.
Hey, exactly. I can't trick you, Matthew. You're no fun. I'm never calling on you again. That's right. Matthew's figured it out. This is where the sun's going to be on March 21st. And guess what? Matthew could probably guess that that's where the sun's going to be on June 21st. And the sun will be in Virgo September 21st. And the sun will be in Sagittarius in winter. So that's the significance of those points, is they're telling you where the sun's going to be at different times of the year. Oh, there's one last definition of the spring equinox. This one's kind of crazy. The spring equinox is also a moment in time. And it might be easier to explain this one in terms of just a globe here, if I could show this to you. In terms of the summer solstice, this will be easier because the exact moment of the summer solstice is the moment when the North Pole is perfectly tilted towards the sun. A day earlier or a day later, this does not point directly towards your camera, which is the sun. You are my sun. You are my shining light. And when this thing points towards you, that's the moment of the summer solstice. But if you think about it, it's not just a day, because during a 24-hour day, Earth is spinning, but it's also sliding about 1 degree through its orbit. So there must be an exact moment, an exact split instant of time at which the summer solstice, the pole points right towards the sun. And that's why if you look on Google, you know, we just passed the spring equinox, so let's find something to look forward to, like the fall equinox. Fall equinox 2020, oops, not 3030, 2020 will do. It'll be Tuesday, September 22nd at exactly 9:30 a.m. So you can wake up, you can do the fall equinox dance, and you can go back to bed if you don't have work, okay? That's the exact moment in time of the fall equinox. All right, Tim, I'm gonna get around to answering your question, just bear with me. It's time to introduce our third coordinate system. That is the equatorial coordinate system. The equatorial coordinate system is a set of coordinates that we use for the entire sphere. It's kind of like latitude and longitude for the celestial sphere. I say that it's for the global sky. They use a set of funky angles. One is called declination. The other is called right ascension. And astronomers, they abbreviate them as dec and RA. That's usually what an astronomer, when we talk to each other, we say, what's the dec and the RA of that star? Declination is like the equivalent of latitude on the sky, and right ascension is kind of like longitude of the sky, but there's some subtle differences. Now, I want to contrast the equatorial system with the horizon system. The horizon system uses altitude and azimuth, and basically, if you look back a few slides here, the idea with altitude and azimuth was it's supposed to be a simple, dumb, common sense, intuitive coordinate system. Altitude is how many degrees up, and azimuth is how many degrees along the horizon, right? So for instance, telescopes will sometimes be designed with an altitude azimuth mount. Let's look at a plane wave 1 meter telescope. This is a gourmet telescope of the sort that I would like someone to buy for me for Christmas. They only cost $200,000, and you can ship them to 90 Eddy Street, apartment 203. I'd be happy to receive it with my truck. Let's see if we can see a picture of one of these puppies kind of in operation here. Ooh, look at those bad boys. You could definitely look at some sweet nebulae with this. And let's see if they show this thing. Oh, look at those, man, dual plane wave. I couldn't even imagine a better gift. Now, notice that these have these fork arms, and they're designed to swivel in altitude and azimuth. So your fork arm there, whoa, get out of here. Get out of here. Okay. Your fork arm can kind of go, that's your altitude. It delivers degrees up. And you can see as they swing around the room here, they're sliding in azimuth. And you'd think, well, man, geez, isn't that all you need? What else could you do? Point up and you point around in the circle. And the thing is, if you want to go out to a telescope with your Grammy and you want to say, Grammy, could you point the telescope at the Orion Nebula? Your Grammy's going to say, well, I don't know where the Orion Nebula is. And you say, that's easy, Grammy. It's 30 degrees in altitude due east. And so Grammy swings the telescope east, 30 degrees up, and there's the Orion Nebula. But what if Grammy's in Florida or California, and you want to call up Grammy and say, hey, could you go out to the telescope and point it at the Orion Nebula? She says, I don't know where the Orion Nebula is. That's absurd. And you say, well, in my sky, it's 30 degrees. Hold on a second. If the altitude of Polaris depends upon your latitude, I'm guessing that all the other star positions also depend upon your latitude. So as you go up and down the globe, the stars will shift their positions And even more infuriating, if you're at different lines of latitude, they will rise and set at different times. It's even more annoying than that, because if you look at the tracks that stars make through your local sky, they make similar tracks sorry, I'm using some terms that you don't know yet. They're similar in tracks to the celestial equator that you see down here. So you can see that as a star rotates to the nighttime sky, it's constantly changing its altitude and azimuth as it rises and sets. That's not helpful, because if you discover your own galaxy and you want to name it the Tim Galaxy or the Matthew Nebula, you want to put your name on it, you need to be able to tell other people where it is so that they don't also try to name it on you. And that's where the equatorial system comes in, because it's sort of a set of fixed coordinates for the sky that everyone can agree on, okay? And this is how we find stars. It's not dependent upon where you are on Earth. Like our definition of latitude, declination is defined as your degrees. We're not going to go north or south. We're going to go positive or negative from the celestial equator, plus or minus from the celestial equator. As an example, Polaris, it would have a declination of, well, it's technically 89.5 degrees, but let's just pretend it's positive 90, all right? Now, right ascension is like longitude, but we can't use the prime meridian as our line of longitude, and that's because during a 24-hour period, the Earth is spinning, and we need something that stays fixed to the sky. So what astronomers have done is they define the the right ascension. I just had a lovely picture that I would like to go back to. Keep that up for later. Maybe I'll drool over it. They define it in terms of the spring equinox. So here's the star Vega. Its declination is positive 38 degrees and 44 arc minutes. Now they show the ribbon going around here, but normally, well, lines of longitude run down like this. So normally you'd start at the spring equinox and you'd go counterclockwise until you got to the nearest point. And this is your right ascension. It's your degrees. Actually, they don't do it in degrees. They measure it in hours measured eastward from the spring equinox. Let's write that down. So the right ascension is defined as the hours, and you can even do minutes, the hours and minutes of a star measured eastward from the spring equinox. We found it helpful to try some sample problems every time we introduce a new definition, just to see if we can put this into practice. And we're going to do that right now. It's also going to speed up part of our lab today. Friends, I'd like to erase. Any objectors should tell me, okay? So let's test out the equatorial system. Let's find the right ascension and the declination of the 4 key points on the ecliptic. In other words, if the spring equinox, if the fall equinox, the summer and winter solstices, if they are points on our celestial sphere, let's find a slightly better picture here, they should also be describable by right ascensions and declinations. And this will take you guys a little bit of work. So let's start here with the spring equinox. I don't know if this is easy or tough. Olivia, maybe I can pick on you a little more. Olivia, do you think you can give a whack at describing the declination or the right ascension of this point? This is the point called the spring equinox.
Okay.
So let's look at our definition for declination. How do we define declination?
Oh, the degrees plus or positive or negative from the celestial equator.
So what would you say then would be the degrees plus or minus from the celestial equator of this point?
So it's pretty close to the pole. The pole, is it the North Pole? That kind of
Hell
goes
no.
through it.
Now,
No?
look, here's the North Celestial Pole,
Okay.
and there's the North Pole. I wouldn't say it's close to either of those poles.
Oh, okay. So the south. Sorry, the South Pole. So like
I wouldn't agree with that either. Here's the South Celestial Pole, and there's the South Pole of Earth. This is a three-dimensional picture, right, Olivia?
Yes.
So there's like a line going through here. So do you see what I mean?
Yeah.
I would say it's close to the South Pole.
Okay. Yeah, I see.
It's on this blue bubble here.
Yep.
Here's a hint. It's on the celestial equator. The celestial equator is this red ring, right?
Yes.
So if you're on the celestial equator, what should your declination be? Look at the definition again.
Oh, it's so positive or negative from the so would it be
What if you're on the celestial equator?
would it be 0?
Yeah, okay.
Okay.
Let's write this down, okay? So, hold on. Stop share. We have proved that the declination is 0 degrees. How about the right ascension? Can you do that?
So that would be hours would it be hours to minutes or hours?
Well, just say hours. Forget about the minutes.
Hours. Okay.
How many hours from the spring equinox are you if you are on the spring equinox?
Oh, 0.
Yeah, but
Okay.
we write it like time. We write it as 0 hours and 0 minutes.
0 hours. Okay.
So I usually write it like a 24-hour military clock.
Okay.
That's how right sections are written. Okay, so that kind of kick-started us. Let's try a more advanced one. Yimmersy, you want to give this a whack?
I can try.
Why not, right? We can always try. Okay, so here's the point called the summer solstice, Yimmersy. And our declination is how many degrees plus or minus from the celestial equator we are. So what's your best Yimmersy guess? There's the celestial equator, the red ring, and there's you. How many
20.
degrees?
From this picture is 23.5 degrees.
But positive 23.5. That tells us that we go up from the celestial equator, okay? All right, so the deck, positive 23.5 degrees. What about the right ascension?
It'll be negative 23.5.
Oh, hold on. Right ascensions are always positive. They're measured in hours, and this is 0 hours, and then we go all the way around this ring. How many hours in a complete spin?
24.
Say that?
24.
Okay, so it looks like we're going a quarter spin. So how many hours would that be?
12.
No, that's a half spin. This is 12.
Oh. 6.
Yes. So from here to there is a quarter turn across the sky. That takes 6 hours. Okay, guys, see if you can speed this up here. Fall equinox. Anyone at all, give it to me straight. I want a deck and I want an RA.
0 deck, 12 RA, 1200 RA.
12 hours. Okay, and while you're at it, whoever that was Adrian?
Yes, that was me.
Okay. Okay, I couldn't remember if it, yes. Okay, how about Adrian, the winter solstice, while you're at it?
Negative 25 degree.
Oh, yep, sorry. Declination is negative 23.5, right?
23.5. I don't know why I have 25.
Negative 23.5. Maybe you forgot to write the 3 and the point.
Yeah, I had 25 instead of 23.5.
Get out of here, OneDrive. You're pissing me off. Okay.
And 18 hours.
Awesome. I forced you to do that one. I pushed that one through because I've got 20 minutes left and there's a couple more bits I got to do for you. And Tim, this stuff that we're about to do now, up to now, Tim, everything you learned about, you also would have learned in 1010. So this is like reinforcement. But this new stuff I'm going to teach you is about sidereal time. And it's very cool, but I left it out of the 1020 class because we had too much to do. And this stuff can be hellishly confusing for students the first time. So I'm going to walk you through this one kind of slow. By the way, right ascensions and declinations are confusing your first time around. But we have a lab today, a lab on the celestial sphere, where I'm going to give you the coordinates of the 10 brightest stars in the sky. You know, it's kind of sad. This is one of those labs that really is just cool to do in person, because you get in a little group of 3 and you each get your own globe and you get to kind of explore the celestial sphere, and it's freaking awesome. I thought about trying to do it with like some kind of computer program. I didn't know if it'd be the same effect. So what I did last semester is I'm going to use my globe. Luckily, I've got one. And we'll kind of do the lab together, and I will try to explore it with my iPhone. Not the same thing as being able to look at it yourself, but such are the times that we're in. We've got to do it like this. There are programs that we could use. They call them planetarium programs. It's a program that has a model of the sky. And I have some like Stellarium and Starry Nights, but I didn't know if it was going to be I think it was going to be a SOB. Just think about it, guys. We have enough trouble printing out papers before we start our lab. Imagining everyone trying to download programs and install them, we'd roll and die before we actually got the lab done. So I think the kind of walkthrough with the iPhone is going to have to be as good as it gets. But let's talk about some issues with time. And I want to share with you a slideshow on astrometry. There is a special branch of astronomy that deals itself entirely with timekeeping, coordinates, and calendar keeping. All of this stuff is astronomical in nature, and it's way confusing and a very intense branch of astronomy. So consider, for instance, what am I doing here? Consider, for instance, that someone's got to keep the clocks and the calendars synchronized to the sky. And this is a difficult thing to do. For instance, the Egyptians, we know from studying hieroglyphics, the Egyptians knew about a 365-day year. So they knew that the sun would wrap up and down the sky about once every 365 days. But if you don't measure it more precisely than that, when you choose your day, your calendar day to be the spring equinox, year after year, because there's actually 365.25 days in a year, the sun will actually start to drift relative to March 21st. So at some point, the Julian calendar was invented to account, they added leap years to try to deal with the fact that it was not exactly 365 days in the year. But that turned out to not be enough too, and the spring equinox kept drifting. And so people had to figure out what was going on with time, and it can be a little bit confusing. Let me start by showing you a picture of a sundial. Sundials are kind of cool. They're a natural method of keeping time by the sun, all right? And I want to give you some fun vocab terms just for kicks and giggles. This stick up here, this is one of my favorite words in the English language. It's a gnomon, okay? The gnomon is the stick that sets up from the dais. And what's going to happen is the sun is going to travel through the southern part of your sky. And as the sun travels through your sky, the gnomon will cast a shadow on the dais. And as the sun moves through the sky, the shadow will move just like the hands on a clock. This is what clocks were before you had your wristwatch. It might be helpful here for me to share with you what the motion of the sun through the sky looks like, because that may not be, And that's my next slide. I anticipate myself. Okay. So on slide 21, for a northern-based observer like a Rhode Islander, on the day of the spring equinox or on the day of the fall equinox, the sun is on the celestial equator. And it will travel the path of the celestial equator in your sky, which you guys have probably already forgotten, but a few moments ago, I asked you to describe the path of this thing. And you found that it rises due east. It reaches an altitude of how many degrees in the southern sky? What's this angle here?
48.
Say that, Tim?
48.
48 degrees. And then it will set back down due west. But as you get into the later months of summer, past the spring equinox, the sun will rise sort of north of east. It'll come up to some angle that's above 48 degrees, and then it will set north of west. At its highest point, the sun will rise, well, this is a geometry problem. This angle here is 23.5 degrees, but this angle here is a little more than that. I'm not going to get into the spherical law of cosines with you because that'll give you the heebie-jeebies, but let's just say that it rises north of east. I can give you this angle. This angle is 48 degrees plus 23.5 degrees. That means at noon on the summer solstice, the sun will be 71.5 degrees above your southern horizon. And then it sets in the west. But I'm just trying to give you a general sense of it all. The sun is kind of rising somewhere in the eastish. It's coming up to 48 degrees-ish, and it's setting somewhere in the westish. Okay, that's the idea that I'm having. So if I go back and I look at my sundial, as the sun rotates through your sky, this shadow will move around the dais and you'll have a 24-hour day. When you keep time by a sundial, you are keeping something that we call apparent solar time. Apparent solar time actually uses the sun to keep time. It's time by a sundial. Let's actually take this as some notes because this is the kind of shit you're going to forget, and I don't want you to forget it, okay? So let me do the notes here. Timekeeping. Here's a thought. You keep time by the motion of the sun through the sky. This is how most humans operate. They like to be up during the day. I'd like to say not all humans operate this way, but most humans like to be up during the day when there is light available to see things, and they like to harvest crops and plant vegetables in their gardens. When you keep time by a sundial, apparent solar time, and that's time by a sundial. I'd like to contrast apparent solar time with something called mean solar time. Mean solar time is time by a mechanical watch. What? You mean the time I keep by a watch or a clock? Or a watch is a mechanical clock. That's right, guys. If you were to keep time by a sundial in your garden, time would not run as smoothly as you think because the sun does not have a perfectly uniform motion across your sky. One of the nice, elegant ways to demonstrate this is to go out at noon every day and take a tripod with a camera on it and point it up towards the sun and snap a photo at noon and just see where the sun's at. If you do this experiment, this is the picture that you will see. So there's probably, I don't know, 1, 2, 3, 4, 5, 6, 7, 8 times. this is maybe 32 observations. I'm guessing twice a month, maybe every 2 weeks, this astronomer went out and photographed the sun at exactly noon. And instead of the sun always being at the observer's meridian, we discover that the sun's position drifts back and forth from the meridian in this wonderful little figure 8 shape. And this figure 8 shape is known to astronomers as an analemma. The meaning of the analemma is interesting. The analemma means that the rotation of the sun across your sky is not perfectly uniform, because if it was, then the sun would have been right on the meridian at noon every time the guy took the picture. By the way, you'll notice that the person left their shutter open on 3 particular days of the year. It's obvious to me which days those are. Is that obvious to you guys? What day is this here?
Summer solstice.
Sorry, one more time, Tim.
Summer solstice.
Summer solstice, yes. And then what would this be?
Spring equinox.
Yep. And that would be the winter solstice, right? So that was very clever of them to leave the shutter open all morning so you could see the sunrise, the sun coming up to the observer's meridian. If you're curious as to why the sun does not take a perfectly uniform journey through the sky, I can explain it to you, and I'm going to try, but I might lose you here. Let me see what I can do. The first issue has to do with the orientation of Earth. The motion of the sun through the sky is different on the equinoxes than it is on the solstices. And let me see if I can demonstrate why to you guys. If you guys are the sun, and this is the Earth, then this might be, say, the spring equinox. On the day of the spring equinox, the Earth is moving through its orbit, and the sun has a slightly north to south trajectory during the day, just due to the motion of Earth around the sun. So it's yearly motion. You know, if this wouldn't happen if the Earth just sat in one position and just spun like this for 24 hours, then the rotation of the sun would be perfectly uniform. But the thing is, the Earth is drifting like this during the equinoxes, which gives the sun a slight north to south motion backwards against your sky. And what's funnier is on the day of the summer solstice, because the north is pointing towards or away from Earth, the sun's drift due to the motion of Earth is entirely east to west. And that slows the motion of the sun down. The other issue is that the Earth does not make a perfectly circular orbit around the sun. You remember it has a perihelion and an aphelion. And as you'll discover later when we study gravity, at perihelion, Earth travels a bit faster around the sun. And this changes the speed that the sun makes through the sky. So the east to west drift is causing the figure 8 shape. And the change in the Earth's speed is why sometimes the figure 8 is kind of little on top and it drags below. So the sun will be at greatest amount 20 minutes off from your meridian on any day. Obviously, when people began constructing mechanical timepieces, if you kept time by a sundial, the length of an hour would be different depending upon the day of the year that you were operating in. And that's not good for an industrial society that needs to have worker bees punching in and out of their Amazon delivery jobs or whatever, right? So we keep, the way you keep time by a mechanical clock through this complex calculation. Back in the day, every little town would have a Swiss clockmaker, and he would be responsible for performing the calculation or writing to someone who knew how, and he would set the master clock of the town, like Big Ben, and everybody else's clocks would get synchronized to that. At some point, when we decided to build big railroads that crossed the United States, it was decided that it might be helpful to break the Earth up into a bunch of time zones, each of which would be 1 hour or 15 degrees in increments. And this helps deal with the problem that the mean solar time in Philadelphia will not be the same as the mean solar time in California, right, Megan? Megan knows all about that because she's got to get her ass up at 7 a.m. to take this class while the rest of us get to sleep in until 9:58. Okay, so just using a hypothetical example, not any real life example for this. Anyways, so at some point it was decided that we should have one master clock. We should keep the clock of the prime meridian, and then all of our clocks would be synchronized to the Greenwich, England's mean solar time. That's what they call Zulu time in the military, right? It's 24-hour time. Normally it's called universal time. It's keeping the mean solar time of Greenwich, England, and then everybody is offset by a time zone. For instance, you'll notice that Rhode Island here, we're about 5 hours behind England, I believe. So we're EST, Eastern Standard Time, is 5 hours behind. Here's the Greenwich Mean Time right there. So 1, 2, 3, 4, 5. And Eastern Time Zone keeps the mean solar time of a city somewhere in the middle. I believe for us, for EST, they choose Philadelphia as our reference city. They wouldn't choose Rhode Island because it's too much on the edge. They wouldn't choose Chicago, it's too much on the edge. Philly's kind of in the middle, all right? Now, there's a lot more I need to say about that because it factors into your homework, but I'm going to leave it there because I got one more little module to do. So let's just say that there is something called UT, universal time, is the mean solar time of the prime meridian, or Greenwich, England. Is it Greenwich? I can't spell sandwich either. W-I-C-H, I think, right? Greenwich, England? It goes by some other names too. They call it GMT, right? That's Greenwich Mean Time. As I was saying, the military, I think they call it Zulu time. It's got different names, or UT. You know, if you're a BBC fan like I am, and Owen Bennett-Jones comes on for the BBC report and says, it's 1300 hours GMT, he's telling you the local solar time at Bush House in London, which is pretty much on the prime meridian, right? Now, you know that Eastern, forget about daylight savings time, we'll deal with that at a later moment, but Eastern Standard Time is UT minus 5 hours, right? So guess what you get if you do 71, our longitude is 71 degrees west, right? If you divide that by 15 degrees per hour, what do you get, Tim? Or anyone with a calculator?
4.73.
Pardon me? A little louder, my friend?
4.73.
And that's hours, right?
Yeah.
That helps you understand why we are 5 hours behind England. 71 degrees of longitude corresponds to a change in 5 hours. All right, I got one last little module before we do our lab today. And unfortunately, it's one of the hardest things I'm going to teach you all day. I know it's coming at the end of class when your brains have just been reduced to mush piles, but you weren't ready for it yet. What if I told you that it's possible to keep time differently than by the sun? What if we kept time by the stars instead? That would be appropriate for some vampire-esque astronomers. Why are we biased towards the sun? Why do we have this solar chauvinism? There are millions of stars out there to choose from. What if we kept time by something different? You discover really quickly that the rotation of the stars is not the same as the rotation of the sun. And this is going to sound nuts, but there's actually two different types of day. For instance, you guys think, how long does it take the Earth to spin on its axis? What'd you say, Olivia? I think you said something.
24 hours?
Yeah, that's what you were told, and you were lied to. It doesn't actually take 24 hours. The spin of Earth is 23 hours and 56 minutes. It's 4 hours short. I'm sorry, 4 minutes short, pardon me. I'm starting to lose it here. Let me show you the diagram that will help you understand this. If you're an observer standing on Earth, this black arrow might represent your meridian. And when your meridian is pointing towards the sun, that's what average ordinary people call noon. The sun's on your meridian at noon. By the way, guys, what's the meridian again? I'm having a moment of doubt that anyone knows what the meridian is, which means I'm talking to no one. That can't be good. What is the meridian? Let's look up the definition.
The meridian is the arc that rises due north and reaches the zenith and sets due south.
Yeah, in other words, the meridian is like here's a picture of the sun going through your sky. The meridian is like the 12 o'clock hand of the sky. It's the north to south line. It's the place when the sun is at its highest in your sky. It's on your meridian, okay? Okay, I just wanted to clear that up. Look at this picture here. When the sun is on a local observer's meridian, then it is noon for them. It's noon for them because the sun is at the meridian at the highest point in the sky. Now, Earth is normally spinning, right? It's spinning as seen from above counterclockwise, and it's orbiting counterclockwise. So Earth orbits in this direction counterclockwise, and meanwhile, it's kind of spinning as it goes. And as it spins, the observer's meridian will spin with it. First here, and then there, and then there, and then there. If the Earth was not moving around the sun, you'd point back to the sun in 23 hours and 56 minutes. Notice here, we've completed a full 360-degree rotation. The problem is, oh wait, am I going in the right direction here? Let me clear this. If Earth is spinning counterclockwise, I apologize. The meridian goes like this, and this, and this, and then this, and this, and this. The problem is, by the time you've completed a 360-degree motion, Earth has moved it a bit in its orbit, and it's not pointing back towards the sun. You've got to rotate an extra 4 minutes to get the sun back to your meridian. That is a 24-hour day. That's what the Egyptians kept track of because they were worshiping Ra or whatever, right? Let's take this down as a note as well. There are two types of day. There is a solar day. This is the one that you know and love. It's a 24-hour day. And it represents, if I could put it cheesily, it's the time for the sun to orbit the sky. It's very much what you would keep if you're using a sundial. There's also a sidereal day. Sidereal means, in Latin, star, so it's with respect to the stars. Let me spell that better for you, because that's a $10 vocab word. The sidereal day is 23 hours and 56 minutes in length. The sidereal day represents the true 360-degree spin of Earth. Now, if we want to keep time by the stars, we'd be keeping a totally different kind of clock in which we either have to measure it in multiples of 23 hours and 56 minutes, or what astronomers do instead, because they're lazy, no one wants to keep track of increments that are 23 hours and 56 minutes, so they redefine the hour, and they force sidereal time to be a 24-hour clock again. A sidereal hour is not exactly the same as a solar hour, but they're close. Okay, I now have to introduce something called local sidereal time. And to do that, we're going to need to make a diagram. This is the last little module we do before we tackle our labs today, so bear with me. Students, do you have this? Okay. I want you to make a picture with me so that I can define how this works. This picture is going to be an east to west based diagram. So get out your little ruler at the edge of your calculator and leave yourself some headroom. And I'm going to go ahead and I'm going to make a line 60 and 30. I want to make a nice, neat diagram here. An old trick you can do to draw a nice, good circle is you can measure out the radius at a bunch of different points. And then you can kind of connect the dots. That's a clever way. Ho, ho, ho. Check that maneuver out. Okay. Because we're going to be tracking the rotation of the sky, it's very important that you follow this diagram to the letter here. We're not going to look at a north to south cut. This time, we're going to do an east to west cut. And I want to strongly suggest that every time you do this, you always put east on the left-hand side, as if you were an observer looking south. And that's because we want the sky to rotate in the same direction as a clock. This line is no longer my zenith because stars don't all cross the zenith, they cross the meridian. This now becomes my meridian line. I'll mark it with an M. I want to be clear about what we're drawing here because it's probably not obvious to you guys. We're drawing a complicated cut through the sky. Here, a picture would be of great service. Where the circle that you just drew with me is kind of like one of these circles. Like imagine a star rising in the east. It's coming up here to your meridian and it's setting down west. This is why I didn't call it the zenith, but I called it the meridian because we could be looking at a cut like so, right? Let's imagine the observer standing here, right? And this is the ground. And I'm going to take a random star, a blue star, and I'm going to put it 15 degrees off from my meridian, which I'm guessing is somewhere around here. Now, I told you that this star is 15 degrees from the meridian. How long ago did it cross my meridian?
1 hour.
Exactly. Because Tim, you know that there's 15 degrees per hour. I'm going to define this angle, known as the hour angle, as the time since the meridian of any star. We abbreviate it HA, or hour angle. And if you defined it as simply as possible, it's time since the meridian. Any object can have an hour angle, depending on where it is in your local sky. I now want to introduce a concept of keeping time, but instead of choosing a particular star, we're going to choose the point called the spring equinox. And instead of following the sun through the sky, we're going to follow the spring equinox through the sky. Let's imagine, class, that the spring equinox just happened to be right there. Can you guys guess with me as to what the hour angle of the spring equinox is in this case? What would you say the hour angle of the spring equinox is here? If you had to make up a number that sounded reasonable.
2.
Sorry?
2.
Well, wait, first of all, who am I talking to so I can look at your face?
Megan.
Oh, Megan, okay. Megan, I don't like 2, and here's why. If 15 degrees is an hour, another 15 degrees would be 2. Like think about to go around the sky, it's 24 hours, right, Megan? So to go down here, this point, by the way, the point that's not on your sky, but it's below your feet at the bottom of the earth, it's called the nadir. The nadir would be like 12 hours. Sorry, my nadir is a little off here. And that means this would be 6 hours, right? So do you see why 2 doesn't fly with me so well? Why don't you try again? Give me another guess.
Three? I'm not sure.
Okay, let's go through the clock together. This is 0 hours for our angle. What's this?
8? Is that right? 8 or 6?
How long does it take a star to go around the entire sky?
24 hours?
More or less. Okay. So how long does it take a star to go from here down to here?
12.
How long does it take a star to go from here over to here?
6.
How long does it take a star to go from here to here?
4.
Thank you. So I'd say maybe this is 4 hours, right? So this is 1 hour. 4 hours. And what you just kept there is what's called local sidereal time. It's the hour angle of the spring equinox. We abbreviate it LST. It's local sidereal time. It is defined as the hour angle of the spring equinox. Sorry, the green doesn't contrast well on the screen here. And what it really is it's time by the stars. And now, Tim, for our final stroke of goodness, we're going to answer the question that you asked me before. Tim asked me, what is the relationship between right ascension and local sidereal time? Tim, do you have the definition of right ascension handy in your books there?
No, I don't.
Oh, you aren't writing this stuff down? You're just freewheeling it?
I do have it.
Oh, okay. What does it say for under right ascension?
Hours and minutes of a star eastward from spring equinox.
And so let's just boil that down to its essence. It's hours east of the spring equinox. Which way is east on the sky here?
Left.
Or let's say counterclockwise. Counterclockwise is east. So according to you, if I wanted to know that star's right ascension, Tim, I would start at the spring equinox and I would travel eastward until I got to said star. That would be the right ascension. Could you tell me what the right ascension of that star was based on the numbers you see here?
3.
3 hours, right. And so let's just write that down below. The right ascension is the hours east of the spring equinox. The fact that you were able to compute that time, Tim, means there's a relationship between all three quantities, which you now can see, the star, the spring equinox, and the coordinate. And the formula goes like this. The hour angle of a star is the local sidereal time minus the right ascension. A formula that I call Ha equals list minus Ra. Now, I'm kind of totally out of time for my lecture today. So I don't have time to do sample problems in this, but you're going to do a sample problem for homework with me on Monday. And oh my gosh, Megan, I hope we both get a better night's sleep because that's going to be confusing. I don't even know if she's here. If I lost her. Oh, there she is. Okay. So this can be some heady, confusing stuff. All right, it's now 3:15. I've gone over by 15 minutes, and I promise to chop your lab appropriately by 15 minutes so that we can wrap up at 4, which is what our target goal is. How'd everyone feel? Do you got that stuff in your notes, and do you have your lab doodad ready to go? All right, so let's transition to the lab room together. Why'd you unplug that lantern last night? All right, let's do this here. Fuck. Oh, man. All right, well, sorry guys, I broke my little number pad. Grading is not going to be fun now. It's all right. I think I can fix it. I just hate these stupid things.
Sorry to interrupt, but I just have a quick question.
Yeah.
I have another class after this on Mondays and Wednesdays, and she was saying that we don't have class on Monday because the 4th of July is being observed.
Dude, totally. Oh, sorry. I just fixed my enter key. Are you guys still with me? All right. Who's talking to me right now? I just got distracted. Who am I talking to?
Oh, my Wi-Fi.
Wait, who's just talking to me just now? Hello? Tim, can you hear me?
Yeah, I can hear you.
Is something weird? Am I weird? Who was I just talking to?
Oh, that was me, Olivia.
Oh, Olivia. Okay. Yes, Olivia. You brought up a great point that I should share with the class, and I totally would have forgot to remind you guys of this.
That's okay. I figured. Sure.
I would have realized it like Sunday night at 11:59. Okay, so thank you, Olivia, for helping scatterbrained old me. In fact, Olivia, you may not have noticed this, but in my syllabus that I gave to you guys, I actually included that. I didn't make a big deal about it, but you'll notice on the schedule here, it jumps from Wednesday, May 20th to Wednesday, May 27th, right? Now, unfortunately, students, you're going to hate this, and I'm going to hate it too, but CCRI has decreed that Monday is a holiday and that our makeup day for that course is Friday, May 29th. I'm sure that's going to suck for some of you. It's definitely going to suck for me. So it's not really like you get a day off. Now, that's important because we only have a very limited number of classes to learn together, and we can't afford to lose a single one. Or I won't get to tell you about cool things like Jupiter.
Wait,
also,
what's the date of the makeup day?
It's next Friday. So next Monday, we don't have class. And instead of meeting on Monday and Wednesday, we're instead going to be meeting on Wednesday and Friday. Now, I take the policy, I follow the official CCRI schedule because they are my employers, and to do otherwise is madness. I'm hoping, is anyone here going to have an issue? You can, of course, watch the video later, but it's not the same if you guys can figure that out. It's not the same as being here live. It's much better because we can talk to each other. So it sounds like everyone's going to grit their teeth and deal with it, right? Olivia, thank you for reminding the class. That's an important detail.
You're welcome. Yeah, I just wanted to double check because I wasn't sure if it was every class or however it was gonna.
No, yeah, it's school-wide. It's a school-wide policy, and
Okay.
I'm going to follow it because of that.
Sounds
Okay, guys, just bear with me here. We're going to do a short portion of this lab where we look up the famous stars with the right ascensions and declinations provided for us. And here's my celestial sphere. I've done this online 2 times in summer 1, and it went okay. we are going to need my phone to work. Hopefully that does work. All right, a couple of things you need to know before we get going. On this sphere, you can see that we've printed stars in these little yellow dots. But I want to tell you about the constellations. So go over here to my first slideshow, and I want you to look around slide 50 or so, 54. Constellations for astronomers are not simply the little stick figures in the sky. Constellations, all 88, they represent areas or territories in the sky. And the territories are weird because they follow the outlines of the stick figures. So anything in this box is considered in the constellation of Orion. Because there are 88 constellations recognized by the International Astronomical Union, the entire globe of the sky has been divided into 88 territories, kind of like the US is broken up into states. If you throw a dart at the US, you're going to end up in one of the 50 states. If you throw a dart at the globe, you're going to be in one of the 88 constellations. Let me see if I can show you what they look like here. I'm going to try that thing where I share my phone. Bear with me because this sometimes works well and sometimes it's a disaster. Stop share screen. Start sharing on the phone. If this doesn't work, I'm going to have to do it with the webcam, and that's going to be much more horrible. Yes. Yes, the gods are with us. Odin smiles on me. Yes. Okay. So, hey, there we go. All right. I don't know. I had a different lamp last time I did this, so I don't know if this is going to work well or not. I have, hold on a second, guys. If I take a piece of paper, actually, you know what I really need is a 3x5 index card. That would be ideal. I can make one. Just a second, students, while I figure this out. Oh. Put you on the tape holder here. Just bear with me for a second. All right. I'll use this slip of paper as a baffle, and hopefully you guys will be able to see what's going on here. Honestly, guys, the lighting is kind of bad. Hold on. I need to figure this out. Maybe a little natural light, too, from the outside will help. Okay. All right, that increased my illumination. This should be a little easier to see now. I'm actually going to turn this off. All right. If you guys look through my globe here, you'll see the celestial equator is where my thumb is here. The celestial equator has a declination of 0 degrees. Now, as I go up I need more hands than I have available to me. As I go up from the celestial equator, each horizontal line, like where my finger is there, that's positive 10 degrees, positive 20. These are your lines of declination. They're just like latitude on a globe, okay? The hours of right ascension are also printed there. Notice that you can see 0 hours. Here you can see 1 hour of right ascension. That's 2 hours of right ascension. And these little tick marks can actually help us get really nitty gritty. The little ticks are 4 minutes of right ascension. The big ticks are 20 minutes. Now the names of the constellations are in blue. the names of the stars, like Alpheratz, are in black. You might be wondering why they're all backwards, because the idea is usually that you look through the globe like you're seeing the curvature of nighttime sky, and that's how you read the names of the constellations and stuff, okay? So we might actually just go backwards because it's a little easier to manipulate it. In the first passage here, oh, by the way, can you guys start off by doing something for me? Please put your name, or type it if you're typing it. And you guys are AS1010. I need you to write, every time you write me, like Olivia, I think, wrote me an email or a text or something saying that she was going to be late to class, which is great. But Olivia, my first thought, because I'm still learning you guys, was, wait a minute, are you in 1010 or are you in 1020? So by putting 1010 in parentheses or putting this stuff there, it helps me keep track of who's in which class. Because the instruction, that's okay. It's something you're not thinking about because you're not in my chair, right? So I'm helping you. All right, so in the first table, we have the celestial coordinates, the right ascension and declination of the 10 brightest, 10 most famous stars in our sky. Our job is to look up the coordinates, find the name of the star and the name of the constellation it's in. The boundaries of the constellations, so while the stick figures of the constellations are in blue, hold on, I'm trying to get more illumination here. While the stick figures are in blue, can you guys see those little faint dotted blue lines? The dotted blue lines are the boundaries of the constellations. Let's just freaking do it, and then you'll get it as we go. So our first star is at 6 hours, 43 minutes, and minus 17 degrees Dec. So let's hunt around for 6 hours. I'm gonna kind of rotate my globe here. Sorry, I know this is irritating. And here's 6 hours. And 6 hours is right on the main line here. To go to 6 hours and 43 minutes, I'm gonna count over to, that's 6:20 right there. That's 6:40. And if they're 4 minutes each, 6 hours and 44 minutes would be there. So that's my line of declination, I'm sorry, of right ascension that I want to be on. Sorry, focus issues. All right. Now, to get our declination, we start here and we have to go down 10 degrees, down 20, and there we are. We'll go back a little bit. Let me try to focus my annoying phone. What's our star?
Sirius.
Sirius. It's the brightest star in the sky, also known as the dog star. And can you tell me what its constellation is?
Canis Major.
Canis Major, the big dog. Okay, so let's get that down. Obviously, Sirius being the brightest star in the sky was going to be number 1. And that's Canis Major. Okay, 7:37 and positive 5. 7 hours is here. That's 20 minutes. Let's see, it's 37. So that's 40 minutes. 4 minutes behind that would be 36. That's 36 minutes. We start at the celestial equator. We go up positive 5 and boom. There's our star, if you can see that. What do you got?
Procyon, Canis Minor.
Procyon and Canis Minor. Since these are Greek names or Roman names, there was no Americanized C like ch, no sound. In Greek and Latin, a C would always be pronounced k, like a K. Procyon and Canis Minor. Okay, next up is 20 hours, 40 minutes, and positive 45 degrees. So I'm gonna have to rotate around my globe here. Obviously, this is a lot cooler when you're doing it yourself instead of watching me do it, but I don't really know what else to do. So there's, oops, excuse me, students. I was looking for this envelope, which I used last time. It was hidden. So, fudge. This is really irritating. So, I lost you guys. All right. So here's 20 hours and the celestial equator. 2040 would be this next tick mark. So we should start somewhere around there. And then our deck is positive 45. So we go up 10, 20, 30, 45. And that's our star. Can you guys read that? That's Deneb in Cygnus the Swan. All right. Next up, 1948 and positive 9. So that's nearby, blissfully. So here's 19, 44, 48. If that's the celestial equator, the declination is positive 9, almost up at positive 10. What's my star? Have you heard of this one before?
Altair.
Altair. And that's in Aquila the eagle. Aquila. Aquila the eagle. So it's Altair in Aquila. I think Altair is like the eye or the beak or something. Okay, by the way, you'll notice that some names of stars are Greek in origin and some are Arabic in origin as well. During the Middle Ages, while Europeans were poking each other with pointy sticks and burning Giordano Bruno at the stake, astronomy was preserved by Arabic mathematicians and astronomers. And many of the names of the stars are still Arabic in origin for that reason. Okay, 513, positive 46. So let's swing this puppy back around here. Here's 5. 13 is about a quarter of the way through the hour. So if you can see my finger shadow, that's 5 hours on the dot. That's maybe 5:13. And now we got to go up positive 46. So 10, 20, 30, 40, and bam. That star is Capella, and it's in the constellation Auriga, the herdsman. In Auriga. Okay. 513 minus 8. So that's the same right ascension as before. It's about a quarter of the way through the hour. Minus 8 drops us down here. And Saif is this star. This is in Orion, of course. And this is the great blue star, Rigel, which I have mentioned in our class in passing. You know, while we're at it, you can see, I'm going to skip ahead here to the, we're also kind of in one side of the globe. Let's pick off this other one at 553 and positive 7. So 553 is almost at 6 hours. And positive 7 is up from the celestial equator. What's our boy there?
Betelgeuse.
Betelgeuse, in the constellation of Orion. Make sure you skip a line, right?
Does Orion have the most to look at?
Well, you know what's awesome about Orion? A couple of thoughts about this since you're asking, Tim. all of the stars in Orion are super damn bright, which is one of the reasons why it's one of the most noticeable constellations. For instance, the 4 stars that make up the shoulders and the feet, Betelgeuse, Bellatrix, Rigel, and Saiph, they all have magnitudes close to 1 or 0, making them among the first rank brightest stars in the sky. And even the stars in the belt are second magnitude, making them the second brightest stars in the sky. So you've got 1, 2, 3, 4, 5, 6, 7 stars already that are super freaking bright. And it's real easy to make the stick figure. Also, Tim, notice it's along the celestial equator. And if you want to imagine where a good position in the sky to be to look at stars, you don't want it along your horizon because then buildings and trees will block your view. But likewise, as you may be familiar with, if you try to tilt back up to look at the zenith, you really have to crick your neck back, and it's very uncomfortable after like a minute of doing that. The ideal vantage point to view things at is maybe about halfway up, 45 degrees. And because the celestial equator in our local sky reaches an altitude of 48 degrees, it's kind of like the ideal height to look at stuff. Now, you can't see Betelgeuse tonight because it's up during the day right now. But as we get into later autumn, fall, when it starts showing up again, you'll notice you can just look south at night and it's right up there on your meridian. It's very easy to see. So it's not that it has more or less stars. It's just that the stars are easier to see, bigger, brighter. It's just ideally primed for good viewing. Let's go to our next star, which is 1410 and positive 19. So I'll rotate over here, excuse me, to 14 hours. Sorry, I know it's tough without a backdrop there. And 1410 would be like 2 little ticks over. Oops, focus. I'm gonna try this again. Let's see if that helps. So there's 14.4, 14.8, so there's 14.10. We'll start at the celestial equator, and we'll go positive 19, positive 10, almost positive 20, and the star is called Arcturus. Arcturus is in this constellation. Hold on. The hole is in exactly the worst place right now. Oh, I'm never going to reach my hand up there. The constellation, it looks like Bootes, B-O-O-T-E-S, but it's pronounced Bootes. He's a herdsman. Bootes. I think the second O has an umlaut. Not every day you get to use an umlaut, huh, guys? All right, so Bootes, the herdsman. Arcturus, you guys can see in your sky tonight if you want to. You've actually probably noticed it and didn't know what you were looking at. One of the brightest stars. So you guys know that I noticed the other day when I was out at night that you can clearly see the Big Dipper, right? And the Big Dipper has a handle that looks kind of like this, right? If you want to find Bootes tonight and you're looking up at the Big Dipper, they say that you arc to Arcturus. So follow the handle of the Big Dipper tonight, follow its curve, and you will see an insanely bright star that's kind of yellowish. That's Arcturus. Now, you probably won't notice the rest of Bootes. Notice that the rest of Bootes, I can't, it's too far away. Bootes kind of looks like a necktie in space. If this is Arcturus, the other stars, they kind of go like this. It kind of almost looks like a necktie or a funky Roman sword or something. It looks something like this. But these stars are really dim and hard to see. Arcturus is super bright. I only mentioned it because I was at a barbecue and it was nighttime and I looked up and I could see it there. It was very nice. Let's look at 1627 and negative 26. So here's 16, 16, 20, 24, 28. And then negative 26. So minus 10, minus 20, minus 26 puts us at Antares. And Antares is famously in Scorpius. Scorpius is a bit lower on your sky, but I think Antares will be up tonight as well. Antares famously is a red star, and that's where it gets its name. Ares is basically Mars in Greek, right? So this star means anti-Mars. It's a star that would be confused with Mars because it's a red star. So if you can see it up in your sky tonight, it'll be low in your horizon around 9 o'clock towards the southwest maybe, I think. Look for anti-Mars, okay? Antares. Scorpius is a faint constellation, but Antares is bright. Lastly, 1836 and positive 39. So here I am at 18. Still figuring out the best way to do this, guys. I can now reach in here a bit. Get that thing tucked under there, okay? Sorry, it's dim. Okay, so 1836. What's our declination? That's 36. What's our dec? Positive 39. 10, oops, 20, 30, almost 40. That's the star Vega. And Vega is in the constellation of Lyra. Oh, scratch the E off. Lyra. Okay, wow. Let's do one more. Let's see if we can find the locations of the planets tonight. Let's see what positions they're in. Now, I'm not gonna, I need to share my screen with you guys, but I'm afraid of deactivating my phone because sometimes if you deactivate the phone, you can't get it back again. So let's just, this is kind of silly, but and trippy. Let's point it at the screen here. And let's find an ephemeris with the coordinates of the planets tonight. One that I like to use is ephemeris.com. I think it's sun. If you type sun to Sedna, it's the first hit. And this will have the coordinates, the right ascensions and the declinations of the planets right now tonight. Let's jot these down. We're just going to do the 5 classical planets. So Mercury, hold on, let me highlight them. Mercury looks like it's at 6 hours and 39 minutes and positive 18 degrees. Oops. So that's its RA, and its dec is positive 18. We'll just keep it real simple here because we're trying to do a stupid job of this. Then it's 4 hours and 20 minutes and positive 17 degrees. Sorry, that was written badly. Let's fix that up. Okay, jotting this down. Let's see here. Mars is 0 hours and 13 minutes and basically negative 2 degrees. I believe Saturn and Jupiter are up tonight. 1943 and 2009. if you can see that. And the declinations are -21 and -20. Can you guys see how these coordinates are very close to each other? What that means to me is they are in conjunction. So this, I'm going to sound like an astrology witch doctor right now, but the planets are in conjunction. Mars and, Jupiter and Saturn are aligned. And that means you're going to get some crazy energy and you're going to be really excited to do your homework, okay? Whenever Jupiter and Saturn are aligned, there's a lot of positive homework energy that happens in class, right? So, okay. I'm just pulling your leg. Doesn't mean anything. All right, so let's go ahead and let's see if we can find what constellations the planets are in. Now, class, they don't print the planets on this globe. Why not? Why wouldn't they print the planets on the globe?
Because they
passes are fixed.
Hold on, someone said, who before Tim, who was that talking to me?
It was me.
Oh, Megan. What did you say, Megan? Because I think you said the right thing.
Because they move?
Yeah. The planets, planetos, is the Greek word for wanderer. The planets wander against the background stars. So we want to see where we catch them tonight in their acts, okay? So 639, positive 18. Let's scroll around here. Sorry, I know it's kind of dim. I lost my good lamp, and now it's harder to do this. Someone took my lamp away. Okay, so 639 puts us over here. And then, 18 puts us up here. That's in the constellation of Gemini. Okay. I think this will be our last act. You know, we'll just get these down and that will, there were other cool parts of this lab, but you can see it's a bit time consuming to do it over the phone here. So 420 and positive 17. Let's see here. 420. It's dark. 420 and positive 10. Positive 20, here's positive 17. Can you guys see what constellation that is?
Taurus.
Okay, 0, 13, -2. That should be right in the celestial equator, so that'll be nice. There's 0, and 13 minutes would be like here, and -2. We're basically in this constellation here. We're in Pisces. Sorry, I know that was tough for you guys to read. Uh, 1943 and -21. Oh, there is one more small act that we need to do after this one. But let's get this done really quick. 1943 is here. And -21, whoa, down into here. And this constellation, it's not Scorpius. Hold on a sec. 1943 is here-ish. And -21 puts us into this constellation. Oh, sorry. It's Sagittarius. Excuse me. 2009 and -20. So there's 29, and then up to -20. And we're in Capricornus. Now, there's one last thing I want to do with you guys, and I'll try to make sure you can see it a little better this time. Actually, if we compare this to a cheat sheet of today's answers in ephemeris.com, you're probably going to notice the constellations don't match up. And I want to talk to you guys about why that is. For instance, they have Mercury in Cancer. We have it in Gemini. They have Venus in Gemini. We have it in Taurus. They have Mars in Aries. We have Mars in Pisces. They have Jupiter in Capricornus and Aquarius. We have it in Sagittarius and Capricornus. They're all shifted by 1 month. Does anyone know why that is? This beautiful globe, it was probably constructed in 1980 or something like that. And it's today 2020. That means this thing is 50 years old. In a period of 50 years, Earth has drifted enough in its precessional motion that it's shifted the positions of the constellations relative to the celestial equator and the North Celestial Pole. This Earth precessional motion, by the way, precession is like a top. That's where something kind of wobbles like this. And it changes the orientations of the skies. It changes the coordinates of the stars. They have to be updated for different epochs. I bet whoever printed this globe in 1980 was using 1950 epoch coordinates, meaning these are almost 100 years old compared to what they are today. That has changed the positions of the stars. This is also why astrology is whack. For instance, let's go around the room here and let's find our B-Day. So because this is the only page we're going to turn in, I want everyone to write down their B-Day here, okay? Mine, for instance, is 4/20, believe it or not. That's my B-Day. And if I were to go by the usual, I want you guys to do this for your birthday, not for mine. If I were to go by the usual astrology mumbo jumbo, I am a Taurus, or maybe on the cusp of. So what I want you to put is your original sign. And I know most of you know this, right? Like, for instance, I don't know, Adrian, what's your sign supposed to be, according to the astrologers?
Libra.
Okay, so mine would be Taurus. So you would write Libra there. I'm going to write Taurus. Let's go to 4/20. This is, the sun moves along the ecliptic here, and there's a bunch of dates printed out here. And I'm going to move the sun, or maybe I'll just use my finger. There's March, and here's April, and here's my birthday, April 20th. You'll notice that whereas I was supposed to be a Taurus, I've now drifted into the constellation of Aries, and now instead of being a cusp between Taurus and Aries, I'm now a cusp between Aries and Pisces. It's not the same. Let's try Adrian's. Adrian, what is your birthday, month and day, like that?
9/25.
9/25. So that's September 25. And you're supposed to be a what again?
Libra.
A Libra. So let's go to September 25th. There's, I'm sorry, it's not very clear, but there's September. And the 25th of September is here, somewhere between 5 and 30th. Wait, hold on. I'm going the wrong direction. September 25th is right there. According to this, you are in this constellation, the constellation of Virgo. So when you were born, the sun was not actually in the constellation of Libra. The sun was in the constellation of Virgo. So let's write your new sign down, right? So my new sign is Aries, but you'll write yours in here as Virgo. So what do you think, Adrian? Are you actually a Libra or are you a Virgo? I don't know either, man. All right, Tim, let's try yours. Let's go on. Tim, what's your B-Day?
September 7th.
Oh, that's convenient for me. All right, so here's September 7th. And so are you also supposed to be a Libra?
I think it's supposed to be a Virgo.
Oh, actually, guess what? You've drifted out of Virgo, and you'll see the dotted, hold on, you probably can't see the dotted line there. Wait, can I see it in the screen? See that blue dotted line? You have now drifted, into Leo. Shoot, you can't see this, can you? You've now drifted into Leo. So you got pushed from Virgo into Leo because of the 26,000 year precession. Remember, we could see even 100 years was enough to shift the positions of the stars. Most of that astrology mumbo jumbo is based off Ptolemy's Tetrabiblos, which was written in like 500 AD. So these are thousands of years out of whack, right? That's been plenty enough time to drift it. I don't know. You know what? We could go around the room, but I think you guys get my point. So in any case, what do you say we just stop there? I was going to do everyone in the class, but there's a lot of you, and there's some Indian food waiting for me on the table, and I'm kind of hungry. So I think maybe we'll just cut this party a little short, if that's okay with you guys, because I'm looking forward to that non-bread. Does everyone have their labs, the page that I asked them to do? This one. Okay. I figured another reason to cut it short might be that we want to see if we're all submitting the materials correctly. So Vanek, earlier we were trying out this procedure with you, right?
Mm-hmm.
You're did you do this on the computer or did you do this on a paper?
I printed out the paper.
Nice. Okay. So you're a good test case then. Let's see if we can figure out how to take a photo that will show up. And by the way, how many of you, show of hands, how many of you put your homework up already? Just 2 peoples? Okay. Let's see how it's looking. Oops, sorry, that's the iPhone share. Share screen. Let's go to Blackboard real quick. I want to see how the class is looking. Oh, I got a chat here. I didn't. Oh, sorry, Nick. I didn't see that until just now. I've got a little section here in my grade center that says needs grading. I didn't grade your labs, but we already looked at those. Let me organize them by assignment. Here's homework 1. So I've got 4 submissions: Timothy, Matthew, Nicholas. Oh, Nicholas just texted. I did. I get it now, Nicholas.
My homework is messed up because I sent the test from the lab last time we met. I can't delete it on my end. Like, you have to delete it in Blackboard.
There's a better way to do this, Megan. I gave you multiple uploads, or at least I should have given you multiple uploads. So what you'll do is, now that you've done homework with me today, you'll just upload over the top of that and it will replace it. Does that seem simpler? Meanwhile, let's check out Matthew's and Nicholas's to see, and Tim's to see how it's looking. So this is, Tim, this is Rockstar because as soon as I call it up, I can see it right there. That's what we would like to have for everyone. Sometimes they appear as links. And maybe the ones who, guys, I've never had to upload this because I'm on the other side of it. So you guys can ironically teach me what the right way to do this is. Matthew, this looks great as well. Matthew, Tim, are you scanning or are you taking a picture with your phone?
I'm using an app on my phone, straight to PDF.
What is that app?
Hang on.
Because maybe that's something other people could get as well.
It's Cam Scanner.
Oh, I actually have Cam Scanner too. I thought that might have been out of date. I have Cam Scanner as well, which is awesome because you can take a picture and turn it right into a PDF. Cam Scanner, I think, was free, or maybe it was like $1.
Yeah, that's still free.
It's still free. So guys, Cam Scanner, can I tell you why Cam Scanner is so awesome? If you have a document, like you're at the DMV, you can take a picture with your phone, and instead of storing it as a JPEG, it'll go right to PDF, so you can send it to government officials or whatnot. It's very helpful. It's been helpful in my life. Matthew, how about you? What did you do?
I just took two pictures, sorry.
And your phone was set to most compatible format, I guess?
Yeah, it flipped the order around, so you're seeing the second page first.
That's okay, because I can click here to see the other one. What's more important is I can quickly look and see that you've got all the right stuff there. So that's what I want to get everybody's looking like. I know some people's came out kind of funny last time. Vinek, do you want to try?
Can you take a look at mine, please? I was having trouble uploading it, but it said it upload now, so I just want you to take a look.
Yep. Okay. Oops. So for those of you who got it all worked out, presumably like Tim and Matthew, you're going to submit your labs in a moment, right? Hold on a second. You already did. Oh, cool. So you guys, before, just so I can like streamline this process a bit, Tim, you're probably good because yours are always looking good. So if you want to just sign out and call it a day, we'll see you. We're not going to see you guys on Monday. Thank you, Olivia, for reminding the class. I'm seeing you guys a week from today, right? And we're going to meet as usual. I want to start the homework close to 10, but sometimes I'm just futzing around and getting shit together. So sometime between 10 and 10:15, I'll blast out a link to you guys, okay? Is that sliding scale okay for you guys? I want it to resemble my normal office hours where I could drift in at any time between 10 and 10:15. Give me a little wiggle room to work with, okay? And luckily, I will always be on time for lecture because I'm coming early during my office hours. All right, so anyways, somewhere between 10 and 10:15. Now, who was I just talking to? Was it Vanek or who or was it Yimmersy? I can't remember who I was just
It was me, I think. I asked you to check for my homework and lab.
Oh, Janabel. Okay. So yeah, let's take a peek and see what we're looking like.
I'm just in my lab right now.
There you are. I have to scroll through all the users actually to get there. It's kind of irritating. So that'll give us a chance to see what everyone's doing. So, oh, Vinek, I can see your picture. It looks good now, but could you think you could rotate that for me so it's not sideways? I'm gonna have to do this to grade your paper, you know?
Okay. I'll try it again when I rotate it, and then I'll resend it.
All right, perfect. Thank you.
Yep.
You guys can see why I want to do this because every single person has a different thing going on. So Tim's looking good. That cam scanner seems to work for him. Matthew, we already checked yours. Yours look good. Nick, I know you're out there in the dark somewhere. I hope you get a camera and join us for reals. Nick, that looks great. Megan's look great. Cool. So everyone's kind of figuring this out. Janabel, let's see what you're up to. Okay, that's awesome. Yeah, I can work with that. Let's see who else is in here. Or is that it? Oh, okay. Does anyone else think they're going to have issues with this? Or I can't remember who was good and who was bad last time. But Vinak, it seems like you figured it out. You just got to, I don't know, stupid thing is frozen. Vanek, you just got to get your rotation down.
I'm trying to use the cam scanner right now.
Okay, yeah, Andrew, we had trouble with you before. Let's.
Yeah.
Where are you? Is there anything up here? Oh, we should have asked Tim before we let him go if he might just be like taking a snapshot of the screen. I'm not sure what he's doing. Okay, well, look, why don't we do this? Let's assume it looks like more people are getting it right than not getting it right. So let's assume, Olivia did as well. Okay, Olivia, we can check yours. Let's assume that people are more or less doing it right. And I'll grade your homeworks this weekend. And if it's irritating to me, I'll write you an email or I'll make a comment and you can fix it. Olivia, let's check. Oh, let's just check these labs real quick. So it looks like 7 of you. Let's just make sure everyone's looking good and then we'll stop there. So Jasmine, I love it. Destiny, I love it. That looks real nice. Timothy's is good. Matthews is good. The doc always works nice. Nick, yours is good. Sorry to put you guys through this, but It's just easier to have the whole class figure this out. All right, Janabelle's is good. And we won't have to keep doing this every class, but just at the beginning to make sure our formats are good. Olivia, yours looks awesome. All right, so I think you guys have got this down now. And Andrew, you keep fiddling with it and we'll make this happen one way or the other, okay? I think though, you guys can see the preview in your box. So if the preview doesn't look good in your box, it probably doesn't look good in my box, right? So that helps you figure out if you're getting it or not. So you think you got this, Andrew? Andrew?
I'm just trying to figure out how to get the cam scanner photos because I'm doing the pictures through my phone for the homework part because I have the lab on my computer.
If I remember how it works, Andrew, you actually go to Cam Scanner. I haven't used it in a little while. And then you take the picture through Cam Scanner rather than through your phone. So I've got Cam.
Yeah, I have the 3 pictures taken on Cam Scanner. I'm just trying to figure out how to get them added to Blackboard now.
I use I don't know if this is helpful, but I use Genius Scan. It's the same concept of the Cam Scanner app. And then I don't know what type of computer you have. I have a Mac, so I just airdrop the file to my computer and then I upload it that way. Or you can email it to yourself. But I find I haven't used CamScan, but I use Genius Scan. And I like the way
the interface. Hey, I'm going to write that down. It's called Genius Cam or Wait, so Genius Scan?
Yep.
Okay.
A little orange app, and it's literally you open it up and then it's as if you're taking a picture and it just scans it for you and it automatically converts it to the PDF and then I just send it to my laptop.
Andrew, I don't think we could beat those instructions, right? That sounds pretty damn easy.
It's super easy. I use it for my other class, so that's how she likes it because she doesn't like any pictures. Same as you, the PDF is a lot easier to read.
It's just a better format. In fact, yeah. I don't mind pictures, by the way. I just need to be able to see the picture. It's got to be favorite. So Olivia, super fucking helpful as always. That's great. So why don't we, Andrew, you want to, and actually that's good to know that other teachers prefer this because they might have figured this out for me. So I see that right here. It's the orange one, right? It's free?
Yep. Yes.
I'm going to get that too. I'm getting that right now. Andrew, so you want to do that? You want to use Genius Scan?
Yeah, I can try it.
Okay.
Yeah, it gives you the option to either send it to like your email or airdrop it or anything like that. It's pretty
super intuitive. Yep. Okay. That sounds like really good advice. So ironically, I need your help, Olivia and friends, because you guys are taking classes all the time, right? I just teach this one class and I don't submit anything. So I don't know what the best practices are. So this is great. This helps me tell other students too. So I'll tell my 1020 class as well. So Genius Scan, Andrew, we're going to do that. Okay.
That's what I used to upload my lab just now.
All right, cool. So Andrew, my personal number is on the syllabus. So I'm going to let you guys go so I can release you from the tractor beam here. But Andrew, if you continue to have trouble uploading that stuff, maybe call me on my phone and you and I will do it. We'll figure it out together, okay?
Okay.
But see if you can get it done. And if you can't, if you're having trouble, call me up and we'll work it out, okay?
Okay. All
right, everyone, great times with you. And I'll see you on Wednesday, 10 a.m.-ish for office hours, right? Okay. Yep. I'm going to stop that recording and I will see you guys